Hello there, and welcome to the Cosmographer. There is a substance in the clouds of Venus that absorbs roughly half of all the sunlight the planet takes in, and after 99 years of photographing it, nobody has been able to say what it is. Number 16 on this list is a population of around 1,000 pulsars that should sit at the center of our galaxy, and the count so far is 1. Number 12 is a comet carrying molecular oxygen that has survived inside it since before the Earth existed. Number 4 is a set of ripples that spread across the surface of the Sun after certain flares, from a source measured 1,000 kilometers beneath it. And the item at the top of this list is the only one that is not out there at all. Over the next 3 hours, we count down 20 phenomena that no working theory accounts for, ordered not by distance and not by strangeness, but by how well we have mapped the ground each one sits on. Get comfortable and settle in. If you enjoy falling asleep to lists like this one, a quiet like and subscribe helps this channel reach more curious minds like you. Because by the end of this list, the mysteries will have stopped being far away. Let's begin at number 20. Number 20. The threads that turn. There is a particular kind of question that gets harder the longer you look at it, and this list is made entirely of those. 20 phenomena, all of them real, all of them measured by working instruments, none of them explained. But the order matters, so it is worth saying plainly how this countdown is arranged before we begin. This list does not descend by distance, and it does not descend by size. It descends by how well we know the neighborhood. Number 20 sits inside the least surveyed structure in the universe, where not understanding something is more or less what you would expect. Every step down from here moves the unexplained thing into better mapped ground. Other galaxies, then our own galaxy, then individual stars we have catalogued and named, then comets we have flown alongside for years, then moons we have landed on, then planets with working spacecraft in orbit right now, then our own moon, then the surface of the Sun, then the space between the Sun and here. And then, at number 1, something closer than any of that. So the territory gets better mapped, and the questions get worse. Each item carries an honest label as we go. Some of these have no candidate explanation at all. Some have several that contradict each other. A few will be settled within a decade by a mission already in flight, and those will be marked as such. None of them will be tidied up with a confidence the evidence does not support. We begin with the largest structures that exist. The universe is not arranged evenly. Matter is gathered into a scaffolding that astronomers call the cosmic web. Broad sheets of galaxies, threads running between them, and enormous empty voids in between. The threads are called filaments, and they are the connective tissue of everything. A typical filament is a few million light-years thick and several hundred million light-years long. If you scaled it down to something you could hold, it would have the proportions of a pencil. Every galaxy you have ever seen a photograph of sits somewhere on this scaffolding. The Milky Way sits on it. Andromeda sits on it. The web is the largest structure there is, and the standard account of how it formed is one of the real triumphs of modern cosmology. That account involves no rotation whatsoever. In the early universe, there were faint ripples in the density of matter, and gravity amplified them. Slightly denser regions pulled in more material and became denser still. Matter collapsed first into sheets, then drained out of the sheets into filaments, then flowed along the filaments into the dense knots at their ends, where galaxy clusters formed. It is a story about gravity pulling things inward along the shortest available path. There is nothing in it that gives a filament a spin. In 2021, a team led by Peng Wang went looking anyway. They used the Sloan Digital Sky Survey, which has recorded spectra for more than 1 million galaxies, and they identified thousands of filaments in that catalog. Then they did something clever. For each filament, they divided the galaxies into two groups, according to which side of the filament's central axis they sat on. And they measured the velocities. The galaxies on one side were systematically moving away from us. The galaxies on the other side were systematically moving toward us. Not dramatically, and not in every case, but consistently, averaged over thousands of filaments. That is precisely the signature you would see if the thread were turning. And the signal behaved the way a real rotation should behave. It was strongest for filaments seen edge-on, which is when a rotation is most visible, and it faded for filaments pointed toward us, which is when a rotation would be hidden. It was strongest for filaments with the most massive galaxy clusters anchoring their two ends. The paper described them as the largest objects known to have angular momentum. That description has held up. The trouble is that nothing predicts this. Angular momentum in the standard picture of structure formation comes from what is called tidal torque theory, and it works beautifully at the scale of a single galaxy. A collapsing cloud of gas sits in the gravitational field of everything around it. That field pulls slightly harder on one part of the cloud than another, and the cloud picks up a twist before it detaches from the general expansion of the universe. That mechanism explains why galaxies spin. It has no obvious extension to an object 100 million light-years long. The scale is the whole difficulty. Light itself takes several 100 million years to travel from one end of a filament to the other. The far end of the thread has no way of knowing what the near end is doing, in any meaningful sense, over the age of the universe. Coherent rotation normally implies communication, or at least a shared origin in a single spinning body. A filament has neither. The proposed explanations are unsatisfying, and they do not agree with each other. One suggestion is that the filaments do not truly rotate at all, but instead carry a kind of shearing flow inherited from the collapse of the sheet they formed inside. That would produce the same signature in a stacked measurement without being rotation in any ordinary sense. Another invokes the massive clusters at each end, twisting the thread between them the way a cloth is wrung. A third and more speculative line argues that the dark matter itself carries a vorticity that cold dark matter is not supposed to have. Computer simulations have since reproduced a filament spin signal, which is genuinely encouraging. But the simulated signal does not cleanly match the observed dependence on filament mass, on filament length, and on viewing angle. The theory produces something that looks roughly right and behaves differently in detail. And then, in 2025, the picture sharpened in a way that made it harder rather than easier. Astronomers reported rotation in a single filament. Not a stack of thousands averaged together, but one individual thread, roughly 15 megaparsecs long, at a redshift of about 0.032. That distinction matters more than it might sound. A stacked signal can, in principle, be an artifact of how the sample was selected. One object turning on its own is much harder to explain away. There is no prospect of watching this happen. At the rotation rates involved, a filament would take far longer than the present age of the universe to complete a single turn. Everything we know about the spin is inferred from a snapshot of velocities, measured once, and it will not visibly change in any human time frame or any civilizational one. What makes this the right place to start is the mismatch between how much we know and how little we understand. This is not an odd rock or a peculiar star. This is the skeleton the entire universe is built on. We can predict its shape. We can predict the spacing of its threads, the sizes of its voids, the statistics of how galaxies cluster along it. Those predictions match the observations to an accuracy that is one of the great successes of 20th century physics. And the same framework has nothing at all to say about why the threads are turning. It is worth sitting with the scale for a moment. The filament our own galaxy belongs to is doing something we cannot account for, and the thing it is doing is the single most ordinary motion in nature. Everything else in the universe rotates. Planets rotate, stars rotate, galaxies rotate, and in each case we can explain where the spin came from. At the largest scale of all, we cannot. But at least the cosmic web is a place we have barely built instruments for. The next item on this list has been stared at by 4 separate X-ray telescopes for more than 10 years, and they still cannot agree on whether it is there at all. Number 19. The line that will not settle. 85% of the matter in the universe has never been identified. That figure is not a guess or a placeholder. It comes from several completely independent measurements that all agree: the way galaxies rotate, the way clusters bend light, the pattern of ripples left in the microwave background, the growth of structure over cosmic time. Every one of them says the same thing. There is roughly 5 times more matter than we can see. It does not emit light. It does not absorb light. And after 90 years of searching, nobody has caught a single particle of it in a laboratory. Which is why, in 2014, a faint line in an X-ray spectrum caused as much argument as it did. 2 teams reported it independently within weeks of each other. One, led by Ezra Bulbul, had stacked the X-ray observations of 73 galaxy clusters, adding the spectra together to beat down the noise. The other, led by Alexei Boyarsky, looked at the Perseus cluster and at the Andromeda galaxy separately. Both found the same thing, an emission line at about 3.5 kilo-electron volts that did not correspond to any known atomic transition. To picture what that means, you need to know what a cluster X-ray spectrum normally looks like. The gas filling a galaxy cluster is at tens of millions of degrees, and it glows in X-rays. Superimposed on that glow are sharp emission lines from specific ions: iron, sulfur, silicon, calcium, argon, potassium. Each one sits at a known energy because atomic physics is extremely well measured. The spectrum is a fingerprint, and it is a fingerprint we can read. The line at 3.5 kilo-electron volts had no fingerprint to match it to. It was faint, roughly 1% of the strength of the potassium and chlorine lines beside it. But it appeared in stacked data from the XMM Newton Observatory, and it appeared in data from Chandra, and it appeared in more than one target. Here is why that mattered so much. Imagine a dark matter particle with a mass of about 7 kilo-electron volts, which decays very slowly. When it decays into a neutrino and a photon, the photon carries away half the particle's mass as energy. Half of 7 is 3.5. And because the decay rate depends only on how much dark matter is present, the line should be brighter wherever dark matter is denser, and it should appear everywhere dark matter is. A particle in exactly that mass range already existed on paper. It is called a sterile neutrino, a fourth kind of neutrino that does not feel the weak nuclear force at all, and therefore interacts with ordinary matter almost purely through gravity. A single unexplained line at exactly the right energy, appearing in the right places, would have been the first direct detection of dark matter in the history of the subject. Not an inference from motion. A photon in a detector carrying the particle's mass written into its energy. It has not held up cleanly. It also has not died. The first serious challenge came from what astronomers call blank sky. If dark matter decays, then the halo of dark matter surrounding our own galaxy should be glowing faintly at 3.5 kilo-electron volts in every direction, including directions with nothing else in them. Careful analyses of blank sky observations found nothing, and set limits that appeared to contradict the cluster detections outright. Then came Hitomi. Hitomi was a Japanese X-ray satellite carrying a microcalorimeter, a detector that measures the energy of each individual X-ray photon by measuring the tiny amount of heat it deposits. It was a generational leap in spectral resolution, capable of resolving the shape of a line rather than merely its presence. It observed the Perseus cluster in 2016 and saw no line at 3.5 kilo-electron volts. It also saw the cluster's ordinary emission with a clarity no instrument had achieved before. Hitomi operated for about a month. On the 26th of March 2016, a chain of attitude control errors caused the spacecraft to spin until it broke apart. The Perseus dataset it left behind remains one of the most analyzed X-ray spectra ever taken. Since then, the field has divided. Some groups reanalyzing the original cluster data found the line at reduced significance. Some found it at the original strength. Some found nothing. It turned out that the result depends uncomfortably on the atomic databases used to model the ordinary cluster emission, and specifically on transitions of potassium and argon, whose strengths are among the least well measured in those databases. There are also perfectly ordinary astrophysical processes that can produce emission near that energy, including charge exchange, in which a bare sulfur ion strips an electron from a neutral hydrogen atom at a shock front inside a cluster. There is one target that ought to settle this, and cannot. The center of our own galaxy holds the highest concentration of dark matter within reach, which means it should be by far the brightest source of any decay line in the sky. It is also one of the most crowded regions in the X-ray sky, packed with binaries, hot gas, supernova remnants, and a supermassive black hole, all of them producing emission lines of their own. Looking for a faint, unidentified feature there is like listening for one sustained note in a room where several hundred instruments are being tuned at once. The brightest place to look is the hardest place to look, and that has been true for the entire decade this argument has run. The successor to Hitomi is called XRISM. It carries the same microcalorimeter technology. It survived, and it has been returning data. It observed a stack of 10 galaxy clusters and looked for an unidentified line. It found none. Its 3 sigma upper limit on the decay rate of a 7 kilo-electron volt particle is around 1 × 10 to the -27 per second. That number is 3 to 4 times tighter than what Hitomi managed at Perseus. It is also still about 5 times weaker than the decay rate the original stacked detection implied. Which means the best instrument ever pointed at this question has not confirmed the line and has not excluded it. It has closed most of the gap and left the remainder open. That is the genuinely odd part, and it is worth stating carefully because it is what makes this an entry on a list of things we cannot explain rather than a story about a mistake. A real astrophysical signal gets stronger as instruments improve. That is what better instruments are for. A statistical fluctuation gets weaker and vanishes because noise does not survive more data. This signal has done neither of those things for more than a decade. It has hovered, always at the edge of what the current generation of telescopes can resolve, always close enough to matter and never close enough to settle. If it is real, it is the first identification of what most of the universe is made of. A sterile neutrino at that mass would be what cosmologists call warm dark matter, which would change the predicted number of small satellite galaxies around the Milky Way, connecting the line to an entirely separate observational tension that has been argued over for 20 years. If it is not real, then it is an unusually persistent artifact of atomic physics we have not measured well enough, hiding in the spectra of the largest gravitationally bound objects in existence. There is a version of this where nobody is wrong. It is possible that the line is produced by ordinary charge exchange in some clusters and not in others, that the stacking amplified it in one sample and averaged it away in another, and that the whole 10-year argument reflects the difficulty of the measurement rather than a fact about the universe. That would be a resolution of sorts. It has not arrived. That mystery, at least, concerns something we already knew we could not see. The next one arrived at a detector bolted to the outside of the International Space Station, and by every calculation we have, it should not have been able to arrive at all. Number 18. 8 particles that should not exist. The alpha magnetic spectrometer weighs about 7.5 tons and is bolted to the outside of the International Space Station. It was installed in May of 2011, carried up on the final flight of the shuttle Endeavour. It very nearly did not go at all. After the Columbia accident, the remaining shuttle flights were reprioritized, and the instrument was removed from the manifest. It was put back by an act of Congress, and it flew on the last mission that could have taken it. Since then, it has measured more than 200 billion cosmic ray particles. For each one, it determines 3 things: how much charge the particle carries, how much it weighs, and, critically, whether the charge is positive or negative. That last measurement is the whole point. A permanent magnet inside the instrument, producing a field roughly 3,000 times stronger than Earth's, bends every incoming particle. Matter bends one way. Antimatter bends the other. 9 layers of silicon tracker record the curve. Antimatter is not rare in cosmic rays, in one specific form. Antiprotons arrive constantly. They are made whenever a high-energy proton slams into a hydrogen atom in interstellar gas, and the collision has enough energy to conjure a proton-antiproton pair out of the vacuum. That process is understood, the rate is calculable, and the calculation matches what the instrument sees. Building a heavier antinucleus is a different problem entirely. An antideuteron is 2 antinucleons stuck together, and it requires that both be produced in the same collision, in the same tiny volume, moving at nearly the same speed, closely enough that they bind. Nobody has ever seen one. Several experiments are searching. Antihelium is harder again. An antihelium-3 nucleus needs 3 antinucleons to coalesce. An antihelium-4 needs 4. And the probability drops steeply with each one you add, because each additional particle has to satisfy the same demanding coincidence of position and momentum. Run the standard calculation, and the expected number of antihelium nuclei arriving at this detector over its entire operating life is effectively 0. Not small. 0, to the precision the calculation supports. And not just for this detector, for any detector anyone could plausibly build this century. The collaboration has reported roughly 8 candidate events. About 6 of them have masses consistent with antihelium-3. About 2 are consistent with antihelium-4. Those results have been presented at conferences rather than published in a refereed journal, which is itself part of the story, and we will come back to it. The antihelium-4 candidates are the difficult ones. Adding that 4th antinucleon makes the coalescence probability drop by roughly another order of magnitude, and there is no mechanism in ordinary cosmic ray physics that gets anywhere near the observed rate. Dark matter has been the most discussed alternative. A heavy dark matter particle, annihilating with its own antiparticle, would produce a shower of quarks and antiquarks, and in principle some antinucleons in that shower could coalesce. But when you carry the calculation through with realistic coalescence parameters, The predicted anti-helium-3 flux still falls short of what has been reported, and the anti-helium-4 flux falls far shorter still. Getting dark matter to produce anti-helium-4 at the observed rate requires model building that most theorists regard as strained, which leaves a much older idea and a stranger one. An antistar would produce anti-helium naturally. A star made of antimatter would burn anti-hydrogen into anti-helium by exactly the same nuclear processes that operate in ordinary stars, and it would blow anti-helium out in its stellar wind, and some of that anti-helium would eventually reach us as a cosmic ray. Unlike the dark matter route, this mechanism makes anti-helium-4 without any difficulty at all, because that is simply what fusion does. Searches through the Fermi Gamma Ray Telescope's catalogue of unidentified sources have flagged a small number whose spectra are consistent with matter meeting antimatter and annihilating. Consistent with is not the same as identified, and nobody is claiming otherwise. But the candidates exist. The problem with an antistar is that it should not exist either. The standard account of the early universe holds that matter and antimatter were produced in almost exactly equal amounts, with a tiny asymmetry favoring matter, roughly one surviving particle of ordinary matter for every billion pairs that annihilated. Everything we see is built from that residue. A surviving pocket of antimatter, large enough to have collapsed into a star, would mean that asymmetry was not uniform across space. That is not a small correction. It is a different early universe. And then there is the deflating possibility, which is that the events are ordinary helium misidentified. The instrument distinguishes matter from antimatter by which way a particle curves in a magnetic field. A rare combination of scattering inside the detector or an unlucky pattern of detector response could in principle make an ordinary helium nucleus appear to curve the wrong way. With 200 billion particles measured, even an extraordinarily rare failure mode will happen a handful of times. That is why the results have not been published. The collaboration has spent years attempting to break its own claim, running the analysis in different ways, checking the detector's behavior against calibration data taken before launch, testing whether the events cluster in energy or in time in any way that would betray an instrumental origin. The events have survived that scrutiny. They have not been confirmed by anyone else, because nobody else has an instrument of this kind in orbit. There is one more detail about this instrument worth knowing, because it says something about how much the collaboration cares about the answer. The alpha magnetic spectrometer was never designed to be serviced. It has no handrails for the purpose, no quick-release fittings, no spare parts stowed nearby. Its cooling system, which keeps the silicon tracker at a stable temperature, began failing after several years in orbit as the pumps wore out. Between 2019 and 2020, astronauts performed 4 spacewalks to cut into the instrument's plumbing, install a new pump system, and reconnect the lines, using tools designed and manufactured specifically for the job, on hardware that had been assumed to be unrepairable. It was among the most complex spacewalking work attempted since the Hubble servicing missions. They did it so the measurement could keep running. An independent check is being attempted. A balloon-borne experiment designed specifically to catch anti-nuclei has been flying over Antarctica using a completely different detection technique, capturing the antiparticle in a target and identifying it from the shower of pions produced when it annihilates. If it sees antihelium, the question closes. If it does not, the argument continues. The candidate events arrive at rigidities of a few gigavolts, which is squarely within the range the instrument was designed and calibrated for. That detail cuts both ways. It means the measurement is being made where the hardware is best understood, which makes the events harder to dismiss. It also means that if there is a subtle flaw in the reconstruction, it is in the most used part of the instrument's range. Set aside the arguments for a moment and consider what a single confirmed anti-helium-4 nucleus would mean. It would say that somewhere within the volume of the galaxy from which cosmic rays reach us, a region of perhaps tens of thousands of light-years, there is a body made of antimatter. Not a laboratory sample. Not a residue. An object. By most reasonable measures, that would be a larger result than a dark matter detection, because it would concern what the universe is made of rather than what one component of it is. For now, there are 8 tracks in a detector above our heads, and the universe is supposed to be made of matter almost everywhere, and 8 particles decline to agree. A handful of particles is a small thing on which to hang a question. The next item is an entire star, in a galaxy you can find with a modest backyard telescope, testing one of the cleanest limits in astrophysics past its stated ceiling. Number 17, the star that shines 100 times too brightly. There is a ceiling on how bright a feeding object can be, and the reason is that light pushes. We do not usually think of it that way, because the effect is small at human scales. But every photon carries momentum, and when a photon strikes a particle of gas, it gives that particle a small shove outward. Pile up enough photons, and the shove becomes a wind. If an object radiates hard enough, the outward pressure of its own light on the gas falling toward it exceeds the inward pull of its gravity, and the gas stops falling. The object cuts off its own food supply. Feed harder and you shine brighter and you push the food away. Arthur Eddington worked this out in the 1920s while studying the internal structure of stars. The resulting number is called the Eddington limit, and for a neutron star of about 1.5 solar masses, it comes out around 10 to the 38th ergs per second. That is roughly 100,000 times the total output of the Sun. It is a generous ceiling. It is also, in principle, a hard one. In 2014, NuSTAR was watching the galaxy Messier 82. NuSTAR is a NASA X-ray telescope with a feature that sounds trivial and is not. It focuses. Focusing X-rays is difficult because X-rays pass straight through ordinary mirrors, and the technique requires grazing incidence optics with the detectors placed a long way behind them. NuSTAR launched in June of 2012 on a rocket dropped from beneath an aircraft, and once in orbit, it extended a 10-meter mast to put its optics the correct distance from its detectors. That mast is why it can see the high-energy X-rays that other telescopes only measure as a blur. Messier 82 is the Cigar Galaxy, about 12 million light-years away, and it is forming stars roughly 10 times faster than the Milky Way. Rapid star formation means many massive stars, and many massive stars means many stellar corpses in binary systems pulling material off their companions. The galaxy is full of bright X-ray sources. While observing it, NuSTAR found a pulsation. One of the bright sources was flickering with a period of 1.37 seconds, steadily and precisely. That is a specific and unambiguous signature. Black holes do not pulse, because a black hole has no surface to which a hotspot can be attached. A regular pulse means a rotating, magnetized neutron star, a body about 20 kilometers across, with a magnetic field so strong it funnels the incoming gas onto 2 small regions near its magnetic poles, so that a beam sweeps past us once per rotation. The source, catalogued as M82X2, was radiating about 10 to the 40th ergs per second at the time. That is roughly 100 times its own Eddington limit. Not near the limit. Not slightly above it. 100 times past it, sustained. 15 years of Chandra observations and repeated new star pointings show it doing this over and over, with no sign of the accretion shutting itself off. Picture what that means physically. There is an object the width of a small city, so dense that a sugar cube of its material would weigh as much as a mountain. It has a companion star beside it, and it is stripping that companion's outer layers away. The stolen gas spirals in, heating as it goes, and by the time it reaches the neutron star, it is glowing in X-rays. The disk of infalling material is not a thin platter. At these rates, it inflates into something more like a thick donut, with a funnel bored down its axis. Out of that funnel pours light, at a pressure that should be holding the entire inflow at arm's length. And the gas keeps coming in anyway. The discovery did more than add one strange object to a catalogue. It overturned a settled interpretation. For decades, astronomers had catalogued ultra-luminous X-ray sources, objects outside the centers of galaxies that outshine any known stellar mass black hole. Because brightness was assumed to track mass through the Eddington limit, these sources had become the leading candidates for intermediate mass black holes, the long-sought missing rung between the 10 solar mass black holes made by dying stars and the millions of solar masses monsters at galactic centers. Finding that rung matters because it bears directly on how supermassive black holes were assembled in the first place. If a source that bright can be a neutron star of 1.5 solar masses, then brightness cannot be used to infer mass. Several more pulsating ultraluminous sources have since been found, and one of them, in the galaxy NGC 5907, appears to be running at around 500 times its Eddington limit. A substantial part of the intermediate mass black hole candidate list has quietly become uncertain. The explanations offered are partial in a very specific way. Each accounts for part of the excess, and none accounts for all of it. The most discussed is magnetic funneling. If the neutron star's field is extraordinarily strong, the infalling gas is channeled into narrow columns at the magnetic poles rather than settling evenly onto the surface. Most of the star's surface is then not being pushed on by the escaping light, and the light itself escapes sideways out of the walls of the accretion column, where it does far less work against the inflow. That helps considerably. But the field strengths required sit at or above the magnetar range, and the way the pulsar's spin rate changes over time does not comfortably match a field that strong. The second is geometric beaming. A thick disk with a funnel down its middle would collimate the radiation into a narrow cone. If that cone happens to point roughly our way, we would measure an enormous apparent luminosity for a source that is intrinsically far dimmer. That works arithmetically. But beaming severe enough to explain a factor of 100 should make these objects extremely rare, and it should distort the shape of the observed pulse more than we see. Then there is the orbit, which is the detail that keeps the problem from closing. Long-term timing of the 2.5-day binary showed the orbit shrinking at a rate of about -5.7 times 10 to the -8th days per day. That is far faster than gravitational wave emission can account for. Something is stripping angular momentum out of the system rapidly, which points to an accretion flow that is more massive and more violent than the standard picture allows. That finding does not relieve the luminosity problem. It feeds it. There is a third idea that sits between the other two. Somewhere in its cycle, the pulsar appears to cross what is called the propeller line, the boundary at which the star's spinning magnetosphere flings incoming material outward instead of drawing it in. On one side of that line, the object accretes and blazes. On the other, it should throw its meal away and dim sharply. M82X2 has been observed at both extremes, dropping and recovering, which tells us the accretion is not steady and that the magnetic field is doing real work on the inflow. It also means the luminosity we quote is a snapshot of a system that switches modes, which makes every average harder to interpret. The star is not simply too bright. It is too bright, intermittently, in a way that changes on timescales of months. There is one more awkward consequence. A neutron star swallowing material at the rate implied by this luminosity should be gaining mass quickly enough to exceed the maximum a neutron star can support and collapse into a black hole on astronomically brief timescales. Yet these sources appear to persist. Either far less material is actually reaching the surface than the brightness suggests, or we are catching several unrelated objects in an extremely short-lived phase, and neither option is comfortable. The plain statement is that a stellar corpse in a galaxy visible through a modest telescope has been violating one of the cleanest limits in astrophysics for at least 15 years, and no model reproduces the full set of observations. That object is 12 million light-years away, and we can still see it clearly. The next item concerns something we cannot see at all, in our own galaxy, in the direction we point our telescopes more often than any other. Number 16, the 1,000 missing clocks. The center of the Milky Way is the most crowded place we can point a telescope at. Within the innermost few light-years, there are millions of stars, packed at densities that would put 1,000 suns inside the volume our own sun has to itself. At the middle sits Sagittarius A star, a black hole of about 4 million solar masses, whose image was released in 2022 after years of work by the Event Horizon Telescope. It is the most studied cubic parsec in astronomy. Every major observatory has spent time on it. Massive stars end as neutron stars. Crowded stellar environments make them in quantity, and the older ones get spun up by feeding off a binary companion until they rotate hundreds of times a second, becoming millisecond pulsars. A millisecond pulsar is one of the most precise clocks in nature. Some of them keep time comparably well to the atomic standards we use on Earth, and they do it for billions of years without maintenance. Every population model built over the last 3 decades makes the same prediction about the galactic center. Given the mass, the age, and the star formation history of that region, there should be somewhere between several hundred and a few thousand pulsars within a few light-years of the black hole. Some estimates run as high as 10,000. Searches have found, within about 15 arc-minutes of Sagittarius A star, 5. Within the innermost region, the few arc-seconds where the prediction is strongest and most confident, the count is 1. And that one is not an ordinary pulsar. It is a magnetar, catalogued as PSR J 1745-2900, which announced itself in 2013 by flaring in X-rays and then turned out to be pulsing in radio waves with a period of 3.76 seconds, sitting about 3 arc-seconds from the black hole. Magnetars are rare. In the general galactic population, they are perhaps 1 neutron star in 1,000. Finding the rare kind, and none of the common kind, in the one place where the common kind should be most abundant, is close to the opposite of what a random draw looks like. This matters far beyond bookkeeping, and it is worth being specific about why. A millisecond pulsar in a tight orbit around Sagittarius A star would be the best test of general relativity available anywhere in the universe. Here is the logic. The pulsar emits a pulse at exactly regular intervals. As it orbits the black hole, those pulses arrive at Earth slightly early or slightly late, depending on where the pulsar is in its orbit, how deep it is in the black hole's gravitational field, and how the black hole's rotation drags space-time around with it. By timing the arrivals over a few years, you could measure the black hole's mass to extraordinary precision, measure its spin, and measure its quadrupole moment, the way its gravitational field departs from a perfect sphere. That last quantity is the prize. General relativity makes a very strong claim about black holes, sometimes called the no-hair theorem. A black hole is completely described by its mass, its spin, and its electric charge, and nothing else. That means the quadrupole moment is not an independent property. It is fixed by the mass and the spin, according to a specific formula. Measure all three separately, and you have a direct test of whether Einstein's description survives in the strongest gravitational field we can reach. Physicists have wanted that measurement for 40 years. The objects that would supply it appear not to be there. For a long time there was a good explanation, and it was the kind of explanation that sounds convincing because it invokes something real. The interstellar gas toward the galactic center is turbulent and dense. Radio waves passing through it get scattered by fluctuations in electron density, taking many slightly different paths of slightly different lengths. The result is that a sharp pulse arrives smeared out in time. If the smearing lasts longer than the pulse period, the pulsation disappears completely, and what should be a clock becomes an unremarkable smudge of radio light. The scattering toward the galactic center is genuinely severe. Sagittarius A star itself is visibly broadened by it, which is why imaging the black hole required observing at very short wavelengths where scattering is weakest. So the pulsars might all be there, spinning away, hidden behind a curtain we cannot see through. Then the magnetar appeared, and it broke the explanation. Because the magnetar was detected, its scattering could be measured rather than assumed. Two things were measured, and they disagreed with each other in an informative way. The angular broadening, how much the source is smeared across the sky, matched Sagittarius A star, confirming a strong scattering screen somewhere along the line of sight. But the temporal broadening, the pulse smearing that actually hides pulsars, was far smaller than the standard galactic center scattering model predicted. Much smaller. That combination has a specific meaning. The amount of pulse smearing produced by a scattering screen depends on where the screen sits between you and the source. A screen right next to the source produces enormous temporal smearing. A screen far from the source and closer to the observer produces angular broadening with very little temporal effect. Very long baseline interferometry located the responsible screen roughly 5 kiloparsecs in front of the galactic center, about a third of the way from Earth. Which means the scattering is not strong enough to hide the missing pulsars. The excuse was checked, and it failed. What remains are alternatives that are all uncomfortable. Perhaps the galactic center genuinely does make magnetars preferentially, and something about the extreme magnetic fields and rapid rotation of stars forming in that environment produces a population skewed away from ordinary pulsars. Perhaps the pulsars are there, but their radio beams are unusually narrow, so they sweep past us and miss. Perhaps many of the neutron stars have already been destroyed, swallowed by the black hole, flung out by close encounters, or fed past their maximum mass by accretion in a region where collisions are common. Perhaps the star formation history is simply different from what we assume, in a way that produces far fewer neutron stars than the total stellar mass implies. The magnetar has, in fairness, been generous with other information. It has the highest rotation measure of any pulsar known, which is a way of saying that the radio light coming from it has had its polarization twisted more severely on the way out than any other pulsars. That twist is produced by magnetized plasma between the source and us, and the size of it tells us that the gas immediately around Sagittarius A star is strongly magnetized, one of the few direct measurements we have of the accretion environment around the black hole. Years of astrometric monitoring have also tracked the magnetar's motion across the sky, and its transverse velocity is consistent with a genuine bound orbit rather than a chance foreground alignment. So the one object we found is real, it is where it appears to be, and it has told us useful things. It has simply not told us where the others went. There is another wrinkle in the same region that suggests the environment is not behaving as expected in more ways than one. Orbiting close to Sagittarius A star is a group of young, massive, bright stars, the S star cluster, and they should not be there. Star formation requires a cloud of gas to collapse under its own gravity, and this close to a 4 million solar mass black hole, tidal forces should shred any such cloud long before it could contract. Yet the stars exist, they are young, and they are on tight orbits. Astronomers have called it the paradox of youth. It has its own set of proposed solutions, none settled. What it establishes for our purposes is that the star formation history of this region is genuinely unusual, which weakens our confidence in the population models that predicted the pulsars in the first place, and also leaves us with no better model to replace them. And then there is a second piece of evidence, from a completely different instrument, pulling hard in the opposite direction. The Fermi Gamma Ray Space Telescope sees an excess of giga-electron-volt gamma rays coming from the galactic center, more high-energy light than the known sources there can account for. There are two leading explanations. One is annihilating dark matter, which would make this the most important observation in physics. The other is an unresolved population of 1,000 to a few thousand millisecond pulsars, blurred together into a smooth glow because the telescope cannot separate them individually. That is exactly the population the radio searches cannot find. So the situation is this: gamma rays that suggest thousands of pulsars, radio surveys that find essentially none, and a scattering explanation for the discrepancy that has now been measured directly and shown to be insufficient. The three do not reconcile, and each of them is a solid measurement. Some analyses of the gamma ray excess find its spatial distribution clumpy rather than smooth, which favors point sources over dark matter. Other groups have contested the statistical methods used to establish that. The argument has been running for more than a decade. The searching continues. Meerkat in South Africa has been observing the region, and the square-kilometer array will follow. The strategy is to search at higher radio frequencies, where scattering matters far less. But pulsars are intrinsically dimmer at those frequencies, so every gain in clarity is paid for in sensitivity. Several dedicated campaigns have now come back with nothing new in the innermost region. It stands as one of the sharpest disagreements between prediction and observation anywhere in galactic astronomy. And it concerns the piece of our own galaxy we have studied harder than any other. The center of the galaxy is crowded and obscured, which is at least a kind of excuse. The next item on this list is a population of stars so simple that their entire remaining history can be worked out on paper, and some of them have stopped following it. Number 15. The stars that stopped cooling. A white dwarf has no fuel left. It is the exposed core of a star that has finished fusing, stripped of its outer layers, held up against its own gravity not by heat, but by a purely quantum effect called electron degeneracy pressure, the fact that electrons refuse to occupy the same state and so resist being squeezed, even at absolute zero. Roughly the mass of the Sun compressed into the volume of the Earth. A teaspoon of the material would weigh several tons. Because there is no fuel, nothing complicated happens next. The object simply radiates away the heat it already has, and gets fainter forever. That process can be calculated from first principles with unusual confidence. You need the mass, the composition, the thickness of the thin hydrogen and helium layers on the outside, and the physics of how energy moves through degenerate matter. Then the brightness follows from the age, and the age follows from the brightness. That reliability made white dwarfs into a clock. The faintest white dwarfs in a star cluster tell you the cluster's age because they are the ones that have been cooling longest. The faintest in the galactic disk tell you when the disk started making stars. It is one of the most trusted dating methods in astronomy, and it is used to cross-check the ages we get by other routes. Then Gaia measured everything. Gaia is a European spacecraft that spent years spinning slowly in space, scanning the sky and measuring the positions of nearly 2 billion stars with extraordinary precision. From position measured repeatedly over time, you get parallax, and from parallax you get distance, and from distance plus apparent brightness you get true brightness. For white dwarfs, which are faint and therefore only visible nearby, Gaia was transformative. The catalogue of white dwarfs with reliable distances went from a few hundred to hundreds of thousands overnight. When those objects were plotted on a diagram of brightness against color, a feature appeared that nobody had predicted. There was a pile-up. At a particular brightness, one that depends on the white dwarf's mass, the high-mass objects bunched together, crowding into a narrow band as though traffic on the cooling track had come to a halt. See how Cheng and colleagues identified it and named it the Q branch. A pile-up on a cooling track means one thing: objects are spending longer at that brightness than the models say they should. But how much longer? To answer that, you need ages, independently of the cooling model you are testing. Astronomers used kinematics. Stars in the galactic disk get gravitationally stirred over time by encounters with molecular clouds and spiral arms, so older populations move faster relative to the local standard of rest. Measure the velocity distribution of the Q branch objects, and you get an age that does not depend on the cooling curve at all. The answer was that a subset of these objects have been sitting there for at least 8 billion years longer than any standard model permits. Roughly 6% of white dwarfs passing through the Q branch experience a delay of 6 billion years or more. 8 billion years is more than half the age of the universe. These objects have effectively been paused for most of cosmic history. To hold a cooling object at constant brightness for that long, you need an internal energy source that switches on late and lasts. Crystallization supplies some of one. As the carbon and oxygen interior cools past a certain point, it begins to freeze, forming an ordered lattice, and freezing releases latent heat in exactly the way water does. That was predicted in the 1960s and confirmed observationally, using the same Gaia data that revealed the Q branch. But the total energy available from crystallization is roughly 1 billion years worth of delay, not 8. The leading candidate goes by the name of neon distillation, and the mechanism is more elegant than it sounds. White dwarfs contain a small amount of neon-22, an isotope with 2 extra neutrons left over from burning the carbon, nitrogen, and oxygen the original star inherited at birth. When the core starts to crystallize, the crystals that form are depleted in neon-22 relative to the liquid around them, because the heavy isotope does not fit comfortably into the lattice. That means the crystals are lighter than their surroundings. So they float upward. As they rise into hotter regions, they melt, and the dense neon-rich liquid they leave behind sinks. The result is a slow, continuous circulation that moves heavy material inward and light material outward. Moving mass inward in a gravitational field releases energy, and unlike latent heat, which is a fixed budget spent once, this can go on for billions of years. Models suggest it requires a neon-22 abundance above roughly 2%, which is well above what an ordinary star of the right mass produces. Which points at mergers. Two white dwarfs that collided and combined would concentrate the heavy isotopes in a way single stars cannot, and the resulting object would be unusually massive, which fits because the Q branch is a feature of the high mass end. Except that white dwarf mergers should leave fingerprints. A merger converts a great deal of orbital energy into rotation and generates strong magnetic fields through a dynamo in the disrupted material. Merger remnants are expected to be rapidly spinning and strongly magnetic. A study of Q-branch objects with confirmed cooling delays found that they conspicuously lack strong magnetism. A competing suggestion is that these are mergers of a white dwarf with a subgiant star rather than with another white dwarf, which could deliver the extra mass without the magnetic signature. Neither version reproduces the whole population. It is worth pausing on the scale of what Gaia did here, because the discovery is a good illustration of how a mystery can sit in plain sight for decades. Before Gaia, the sample of white dwarfs with distances good enough to place them accurately on a brightness diagram was small, and the high-mass white dwarfs, which are rarer than the ordinary sort, were represented by a handful of objects scattered across a wide region of the plot. With 100 times more objects and much better distances, the scatter resolved into structure, and the structure turned out to have a stall in it. Nobody had to build a new telescope or invent a new technique to find this. The pileup had always been there. There had simply never been enough dots on the page to see it. There is also a wrinkle in the composition. Some of the most massive white dwarfs are thought to have interiors made not of carbon and oxygen, but of oxygen and neon, produced when the original star was massive enough to burn carbon before shedding its envelope. Oxygen-neon interiors crystallize at different temperatures and separate their isotopes differently, which changes the distillation calculations substantially. Establishing which Q-branch objects have which interior composition is not something that can be read off a spectrum, because the interior is buried under layers that hide it. That uncertainty is one of the reasons the models have room to disagree. There is one further consequence of the neon idea that is worth noting, because it is genuinely strange. A star whose brightness stays nearly constant for 8 billion years, instead of steadily fading, would maintain a stable zone of comfortable temperature around it for that entire span. Work has been published on what long-lived habitable zones around distilling white dwarfs would look like. Whether anything could take advantage of one is a separate question. That the arrangement is physically possible is not. The uncomfortable part is what this does to the clock. White dwarf cooling ages underpin a set of results about when the Milky Way started forming stars and how old its oldest components are. If an unknown fraction of massive white dwarfs are running 8 billion years behind schedule, then some of those ages are wrong. And because we cannot yet identify which objects are delayed except statistically, we do not know which of the ages to distrust. Those are single stars, and single stars are allowed to be strange. The next item is not one object behaving oddly. It is every single one of them, without a known exception. Number 14. The second population inside every cluster. A globular cluster is a sphere of stars, a few 100,000 of them, sometimes more than 1 million, bound together by their own gravity and orbiting the Milky Way as a unit. There are around 160 of them associated with our galaxy. They are old, typically 12 to 13 billion years, which makes them among the oldest structures we can date. Through a telescope, they are one of the genuinely beautiful sights in the sky, a dense golden knot that resolves into individual points as the magnification rises. For most of the 20th century, they were also the textbook example of a simple stellar population. The assumption was that all the stars in a cluster formed at the same time, from the same cloud of gas, with the same chemical composition. That assumption was not idle. It made globular clusters into a laboratory. If you know that a group of stars shares an age and a composition, then any difference between them must be due to mass alone, and you can test the theory of stellar evolution directly. Clusters were used to calibrate that theory, to establish the distance scale, and, because their ages set a floor on how old the universe must be, to constrain cosmology itself. In the 1990s, cluster ages were the strongest argument that the universe was at least 12 billion years old, at a time when some cosmological models wanted it younger than that. The assumption is wrong. Every globular cluster that has been examined spectroscopically in detail contains at least two chemically distinct populations of stars. The signature is called the sodium-oxygen anticorrelation, and it is unmistakable once you know to look for it. Take a sample of stars in a cluster and measure sodium and oxygen in each. In an ordinary population, the two would track each other because both are made in the same places by the same processes. Instead, they run inversely. The stars with the most sodium have the least oxygen, and the stars with the least sodium have the most, in a smooth, continuous relationship across the sample. Running alongside it are correlated variations in nitrogen, carbon, magnesium, and aluminium. Together, the pattern is a specific fingerprint. It is what you get when material has been through the interior of a star and processed by hydrogen burning at high temperature, by the carbon-nitrogen-oxygen cycle, which converts carbon and oxygen into nitrogen, and by proton capture on neon and magnesium, which builds sodium and aluminium. There is one crucial constraint. Iron is almost identical across both populations in nearly every cluster. That single fact eliminates supernovae, because a supernova would inject iron along with everything else. Whatever processed this material did it without exploding. So one group of stars in each cluster is built partly from the exhaust of an earlier group. That would be an interesting piece of stellar archaeology, except for the arithmetic. The stars that could plausibly do the processing eject only a small fraction of their mass in the correct chemical state. The main candidates are massive asymptotic giant branch stars, which burn hydrogen at the base of a deep convective envelope and shed their outer layers gently, fast-rotating massive stars which throw material off their equators, and very massive stars of around 1 million solar masses, which are hypothetical objects invoked mainly for this purpose. Whichever you choose, the yield is low. To build the observed second population, which in many clusters accounts for half or more of the stars, the first generation must have been 10 to 100 times more massive than the cluster is today. Which means the cluster must have lost the overwhelming majority of its original stars. Some loss is genuinely expected. Clusters orbiting the galaxy are stretched by tidal forces, and stars evaporate from the outskirts over billions of years. But we are not talking about some loss. We are talking about 90 to 99%. And if that happened, the halo of the Milky Way should be filled with the discarded first-generation stars, carrying their distinctive composition. It is not at anything close to the required numbers. Surveys have looked. The chemistry refuses to cooperate as well. Models of asymptotic giant branch stars that get hot enough at the base of the envelope to destroy oxygen efficiently also destroy sodium. That gives a correlation between the two elements rather than the observed anti-correlation, the exact opposite of the data. Fast-rotating massive stars produce material with roughly the right composition, but they eject it at speeds that make it hard for a cluster's weak gravity to retain. Very massive stars work chemically and have never been observed. There is a further pattern that no single polluter explains. The extent of the anti-correlation, how wide the spread in sodium and oxygen is, varies from cluster to cluster, and it correlates with the cluster's mass. more massive clusters show wider spreads. Recent work has extended that to a clear relationship between cluster mass and the total spread in carbon, nitrogen, oxygen, and sodium together. Any successful model has to reproduce not just the effect, but its dependence on mass. This is also not a subtle result, visible only in a handful of bright giants. Hubble ultraviolet photometry of clusters separates the populations cleanly by color, because nitrogen-rich stars have stronger molecular absorption bands in the ultraviolet. Plot a cluster in the right filters, and it splits into distinct sequences you can see by eye. It is a structural fact about every one of these objects. It also shows up in a place astronomers had been staring at for half a century without understanding what they were looking at. The horizontal branch is a feature on a cluster's color magnitude diagram formed by stars burning helium in their cores, and in some clusters it stretches unusually far toward the blue. Nobody could explain why some clusters had extended blue horizontal branches and others did not. It turns out that stars enriched in helium, which the second population is expected to be, since the polluting material has been through hydrogen burning, evolve onto the horizontal branch at hotter temperatures. The strange horizontal branches were the multiple populations announcing themselves photometrically, decades before anyone had the spectroscopy to name the cause. The universality is the part that resists every attempt to make this a special case. The anti-correlation is so consistently present that it has been proposed as the defining characteristic of a globular cluster, the property that distinguishes them from open clusters, which are younger, less massive, and do not show it at all. If you find a spherical group of old stars and it shows the sodium-oxygen anti-correlation, it is a globular cluster. If it does not, it is something else. That is a useful classification rule. It is also an admission we are using an unexplained phenomenon as a definition. Omega Centauri, the most massive cluster in the Milky Way, is worse still. It has a genuine spread in iron as well, and is now widely thought to be the stripped remains of a dwarf galaxy that the Milky Way consumed, rather than a true globular cluster. That explanation works for one object and not for the other 150. There is a clue in the young end of the population. Massive young clusters in nearby galaxies, at ages of tens or hundreds of millions of years, do not show the effect. Either it is a phenomenon of the early universe, requiring conditions that no longer exist, or it takes time to appear. Distinguishing those two possibilities would narrow the field considerably. It has not been done. Euclid is now imaging clusters across wide fields and down to faint magnitudes, and detailed theoretical work has already been published on how multiple populations should appear in its filters. It may deliver the first genuinely population-level statistics rather than cluster-by-cluster studies. 20 years of concentrated work has established the phenomenon thoroughly and has not produced a model for it. That problem is about where material came from. The next one is about material that should have been destroyed and somehow was not. Number 13, the element that should have burned away. Lithium is the third element on the periodic table and one of the most fragile things in nature. It is a small nucleus, loosely bound, and when it encounters a proton at a temperature of about 2.5 million degrees, it captures that proton and immediately falls apart into two helium nuclei. 2.5 million degrees sounds enormous, but by stellar standards, it is nothing. It is a temperature reached a modest distance below the surface of almost any star. That gives a very clean prediction for what happens to lithium in a star's outer layers. As long as those layers stay put, the lithium survives. The moment the star begins to circulate them downward, the lithium is destroyed. When a sun-like star exhausts the hydrogen in its core and swells into a red giant, that circulation is exactly what happens. The outer envelope becomes deeply convective, overturning like a pot on a stove, carrying surface material down to depths well past the lithium burning temperature and bringing processed material back up. The mixing is thorough, and it is not optional. Within a relatively short time, the star's surface lithium should be reduced to a small fraction of what it started with. The observations agree. Take a survey of red giants and measure lithium in each, and the overwhelming majority show exactly the depletion the models predict. It is one of the reliable confirmations that we understand how convection works inside evolved stars. About 1% do not. These are the lithium-rich giants, and some of them are not merely rich, but carry more lithium than the interstellar gas they formed from. That distinction matters enormously. A star with a bit more lithium than expected might have mixed less efficiently. A star with more lithium than its birth cloud had cannot be explaining anything by inefficiency. The lithium is not a leftover. It is new. Something inside that star made it, recently, and got it to the surface. For decades, these were a handful of curiosities, first noticed in the 1980s, easy to set aside as oddities. Then the large spectroscopic surveys arrived. LAMOST, a wide-field telescope in Hebei province in China, can record 4,000 stellar spectra at once. GALA, working in Australia, has taken hundreds of thousands more. Together, they have turned up more than 10,000 lithium-rich giants. What was a curiosity is now a population, and populations demand explanations. There is a real clue in the data, and it came from an unexpected direction. Asteroseismology is the practice of reading a star's internal structure from the pattern of its surface oscillations, in much the same way a geologist reads the Earth's interior from earthquake waves. Applied to red giants, it can distinguish two kinds of star that look identical from outside, those still burning hydrogen in a shell around an inert core, and those that have already ignited helium in the core and settled into a stable phase called the red clump. When lithium-rich giants were sorted by that criterion, they were not distributed randomly. The extreme cases, the super-lithium-rich stars, with 1,000 times more lithium than expected, turned out to be almost exclusively red clump stars. And not just red clump stars, but young ones, within a few tens of millions of years of the moment their core helium ignited. Some analyses put the window far tighter still. That moment has a name. It is called the helium flash. When a low-mass star's core becomes degenerate and hot enough, helium ignites all at once rather than gradually, in a runaway that briefly releases energy at a rate comparable to an entire galaxy of stars. It is one of the most violent events in an ordinary star's life. And according to standard models, none of it reaches the surface. The energy is absorbed internally by lifting the degeneracy of the core, and the envelope above notices nothing. A star goes through the helium flash, and its outward appearance barely changes. So we have a strong statistical association between fresh surface lithium and an event that is supposed to be perfectly insulated from the surface. The proposed mechanism goes back to the 1970s and is called the Cameron-Fowler process. Helium burning produces beryllium-7. Beryllium-7 decays into lithium-7 with a half-life of about 53 days. If the beryllium can be carried outward fast enough, faster than 53 days, and faster than it would be destroyed at intermediate depths, then it will decay in the cool outer envelope, where the lithium it becomes can survive. The chemistry works. The transport is the problem. You need something to move material outward through a stellar interior on a timescale of weeks, and standard convection in that region does not do it. Candidate transport mechanisms include internal gravity waves excited by the flash itself, which could propagate outward and drive mixing, and various forms of extra mixing invoked for other purposes. None of them is derived cleanly enough to predict why 1% of giants do this and 99% do not. It is worth appreciating what astroseismology had to accomplish to produce this clue at all. The red clump is the single most densely populated region of the diagram astronomers use to plot evolved stars. A red clump star and a hydrogen shell-burning giant of similar brightness sit almost on top of each other, and no amount of ordinary spectroscopy separates them reliably. The difference is entirely internal. One has a helium-burning core, the other does not. What distinguishes them is the pattern of sound waves trapped inside, which show up as tiny brightness variations at the surface, measured over months. Kepler and later TESS provided those measurements for tens of thousands of giants. Cross-matching that catalogue against the Lamoste lithium measurements is what turned a scattered anomaly into a pointer at one specific moment in a star's life. The rival explanation is external. If a giant swallows a planet, or a small companion star, the accreted material carries its own lithium. Planets do not get hot enough inside to destroy it, and dumps it straight into the envelope. That would produce a lithium-rich giant with no new nucleosynthesis at all. To test it, astronomers monitored the radial velocities of more than 1,000 giants, looking for the wobble that betrays a companion. The result was not a clean yes. Some lithium-rich giants are binaries. Most are not, and the binary fraction does not obviously differ from ordinary giants. Population synthesis of a specific merger channel, a helium white dwarf spiraling into a red giant, produces lithium-rich objects at roughly the observed rate, which keeps that root alive alongside the helium flash. Some lithium-rich giants also show excess infrared emission, indicating a shell of dust and therefore a recent ejection of mass, which ties the lithium to an episode of surface instability and does not obviously favor either explanation. There is a final irony worth sitting with. Most of the lithium in the universe was not made in stars at all. It was made in the first few minutes after the Big Bang, along with hydrogen and helium, and stars have been slowly destroying it ever since. The lithium in a battery is, in the main, older than every star in the sky. And a small number of dying stars are quietly making more of it, in a way we cannot yet write down. Stars are difficult, and we cannot open them. The next item on this list is an object we flew alongside for 2 years, sampled directly, and still cannot explain what we found inside it. Number 12. The oxygen that should not have survived. Rosetta reached Comet 67P Churyumov-Gerasimenko in August of 2014, after a journey that reads like an endurance test. 10 years in flight. 3 gravity assists at Earth, 1 at Mars. 2 asteroid encounters along the way. 31 months in hibernation, powered down to almost nothing while it coasted through the outer solar system, with an alarm clock set to wake it up in January of 2014, and no way to check in the meantime whether the spacecraft was still alive. It woke up. And then it did something no mission had done before. It flew in formation with a comet for 2 years, through the comet's closest approach to the Sun and out the other side, watching the nucleus wake up and go back to sleep. The instrument that matters for this story is called Rosina, a mass spectrometer that sampled the gas streaming off the nucleus continuously for the length of the mission. A mass spectrometer works by ionizing whatever it takes in and sorting the resulting ions by mass. Rosina was good enough to distinguish molecules differing in mass by a few thousandths of an atomic mass unit, which is what allowed it to separate species that lesser instruments would have blurred together. Between September of 2014 and March of 2015, it detected molecular oxygen. Not oxygen atoms. Not water, not carbon dioxide. O2, the diatomic molecule, the thing in the air. The local abundance ranged from about 1% to 10% relative to water, with a mean around 3.8%. That made molecular oxygen the fourth most abundant species coming off the comet, after water, carbon dioxide, and carbon monoxide. The team's first assumption was contamination. It is the correct first assumption. Spacecraft carry their own oxygen in tanks, in materials, in surfaces that outgas for years. Finding the most reactive common molecule in the universe pouring out of a 4-billion-year-old ice ball is not a result. It is a reason to check the instrument. Consider what is being claimed. Molecular oxygen is aggressively reactive. In the cold, dense molecular clouds where comets are assembled, it should react with hydrogen and with the surfaces of dust grains on short timescales, ending up locked away as water or hydrogen peroxide. Decades of radio searches found almost none of it in interstellar space, and where it was found, at parts per million rather than percent. Nobody had included it in models of cometary ice because there had been no reason to. But the checking went on for months, and the contamination explanation did not survive. The reason was not the abundance. It was the correlation. The oxygen tracked the water almost perfectly. Same spatial distribution around the nucleus. Same variation over time, across seasonal changes, on a body with an unusual bilobed shape and a complicated rotation that swung different regions into sunlight in a complicated sequence. When water production rose, oxygen production rose with it, in a nearly constant ratio, for months on end. That single fact ruled out the obvious alternative. If the oxygen were being manufactured on the surface in real time, by ultraviolet light or energetic particles splitting water ice into hydrogen and oxygen, a process called radiolysis, then it would track sunlight, not water. It did not. It behaved like what chemists call a parent species, something frozen into the nucleus at the moment it formed and released intact as the surrounding ice sublimated away. Which means it is primordial. It has been sitting inside that nucleus for about 4.5 billion years, since before the Earth had assembled itself, and nobody can say how it got there or how it survived. Picture the scene from the spacecraft's position. Rosetta is a few kilometers off a nucleus 4 kilometers across, made of 2 lobes joined at a narrow neck, a shape that turned out on close inspection to be 2 separate bodies that had merged at walking pace early in the solar system's history and never fully compacted. Sunlight is warming one hemisphere. Jets of gas and dust are rising from the illuminated regions, faint and steady, invisible except where they catch the light. The spacecraft is drifting through the outer edge of that outflow. Inside, a small instrument is ionizing a whisper of gas, a few molecules at a time, and sorting them. And in the resulting histogram of masses, there is a peak at 32 atomic mass units that has no business being there, from ice that was assembled before the sun had finished forming. The oxygen was not the only surprise the comet delivered, and the others sharpen rather than soften it. Rosetta found molecular nitrogen, which is also difficult to trap in cometary ice, and which pins down the formation temperature. It found phosphorus and glycine, the simplest amino acid, and a range of organic molecules that had previously been detected only in interstellar clouds. It measured the ratio of deuterium to ordinary hydrogen in the comet's water and found it 3 times the value in Earth's oceans, which argued against comets of this family having delivered our water. Taken together, 67P became the most thoroughly characterized primitive body in the solar system, and the picture it painted was of an object assembled cold, gently, from material that had never been strongly heated, which is precisely the environment in which molecular oxygen is hardest to explain. There is also the matter of the two lobes. If the nucleus is genuinely two bodies that merged, then the ice inside them may record two separate formation histories from two locations in the early nebula. The oxygen abundance measured over the mission varied by a factor of about 10 as different regions became active, while its ratio to water stayed comparatively steady. That is the behavior of a component mixed uniformly into the ice, not one concentrated in patches, which makes the merger complication less useful as an escape route than it first appears. The proposed origins each fail on a specific point. Radiolysis of water ice by cosmic rays in the protosolar nebula can produce oxygen, but the amount required implies a finely tuned irradiation history that the comet's other properties do not support. Formation in a warm, dense region of the nebula, where oxygen chemistry is favored, conflicts with everything else this comet says about having formed cold and stayed cold. Trapping oxygen in amorphous water ice at very low temperature works chemically, but it predicts a particular relationship with other trapped gases like argon and nitrogen, and the observed relationship is different. And then someone went back to the archives. In 1986, the European Giotto spacecraft flew past Halley's Comet at high speed and returned mass spectrometry data that had been analyzed with the tools of the time. A reanalysis, decades later, using the knowledge that molecular oxygen might be present, found evidence of it at a comparable abundance. Which means this is not a peculiarity of 67P. It appears to be a general property of cometary ice. The wider implication is one astronomers would rather not have. Molecular oxygen in the atmosphere of a distant planet is treated as one of the strongest indicators that something living might be producing it, because on Earth, oxygen is maintained almost entirely by photosynthesis and would otherwise react away. A comet full of oxygen that was made without any biology at all, by a process nobody has identified, is a reminder of how much has to be understood before an oxygen detection elsewhere can be interpreted. Rosetta ended its mission on the 30th of September 2016 by descending slowly onto the nucleus and transmitting until the moment of contact, at a landing speed comparable to a slow walk. The instrument kept sampling the whole way down. The Philae lander deserves a line here as well. It separated in November of 2014, and its anchoring harpoons failed to fire, so it bounced twice across the surface before coming to rest wedged in shadow against a cliff. With almost no sunlight reaching its panels, it had only its primary battery, and it worked for about 60 hours before falling silent. In that time, it returned surface measurements that independently confirmed the chemistry the orbiter was sampling from a distance. 67P at least held still while we studied it. The next comet on this list erupts several times a year, and nobody can say when. Number 11. The comet that erupts on no schedule. Comet 29P Schwarzmann-Wachmann 1 was discovered in 1927, and it was clear almost immediately that it did not behave like a comet. Comets are supposed to be visitors. They fall in from the outer solar system on long elliptical paths, brighten as they approach the sun, unfurl a tail, and recede. 29P does none of that. It sits in a nearly circular orbit just outside Jupiter, between about 5.5 and 6 times the Earth's distance from the Sun, and it stays there. It never comes closer. It receives around 3% of the sunlight Earth does, which is not enough to make water ice sublimate at any meaningful rate. By every reasonable expectation, an object in that orbit should be inert. It is also large. Estimates put the nucleus at roughly 60 kilometers across, enormous by cometary standards, where a few kilometers is typical. That size is difficult to pin down because the object is permanently surrounded by its own dust, so the measurement has to be teased out of thermal infrared observations by modeling away the coma. It belongs to a population called the centaurs, bodies that have drifted inward from the Kuiper belt and are on their way, over a few million years, to becoming ordinary short-period comets. Centaurs are transitional objects. Their orbits are unstable, shuffled by close encounters with the giant planets, and their dynamical lifetimes are brief compared with the age of the solar system. 29P is a snapshot of a process caught partway through. And it erupts. Historically, about 7 times a year, the comet undergoes a major outburst in which its brightness jumps by 2 to 5 magnitudes, a factor of 6 to 100, within a matter of hours. Material is thrown off the nucleus and expands outward as a shell of dust, and the resulting coma can grow wider than Jupiter. Between outbursts, it maintains a persistent low-level activity that nothing else at that distance shows. The general mechanism is understood well enough that astronomers use the word cryovolcano for this object without much argument. Water ice does not sublimate out there, but carbon monoxide does. Sunlight warms the crust, volatile ice below the surface turns to gas, pressure builds in a subsurface pocket until the overlying material fails and the interior sprays out as cryomagma, a slurry of gas, ice grains and dust. There may be a second energy source as well, amorphous water ice, laid down at very low temperature in a disordered state, will spontaneously reorganize into ordered crystalline ice when warmed past a threshold, and that transition releases heat and liberates trapped gas. It is an exothermic process, which means it can run away, one patch triggering the next. Observations have identified at least 6 discrete active sources on the nucleus, concentrated on one hemisphere, on a body that rotates roughly once every 57 days. What cannot be explained is the timing. The outbursts are not periodic. They are not correlated with distance from the Sun, because the orbit is nearly circular and the illumination barely changes over the comet's 15-year year. They correlate only loosely with rotation, which would be the natural suspect if particular vents were being switched on as they turned into sunlight. Some outbursts happen singly. Some come in clusters, packed together. In late September of 2021, the comet produced 4 outbursts in about 2.5 days. The first began on the 25th. The last finished on the 27th. Each successive event was more energetic than the one before, and the most intense was roughly 15 times the energy of the first. By the 28th, the comet had reached around magnitude 11, possibly its brightest in 4 decades, and photographs taken over the following weeks showed the expanding dust laid out in a spiral resembling a snail shell, the shape produced when a jet fires from a rotating body, so that the ejected material is wound outward as a coiling stream rather than a simple sphere. Coordinated observations during that event, using millimeter wave and infrared instruments, measured the outgassing directly and characterized how the carbon monoxide behaved. The results constrain the models. They do not settle them. It is worth measuring this activity against the standard by which we usually judge such things. Io, the innermost large moon of Jupiter, is the most volcanically active body in the solar system by an enormous margin, driven by tidal heating from being squeezed between Jupiter and its sibling moons. After Io, the candidates thin out quickly. 29P is generally reckoned to be next, an object in the cold outer solar system, with no tidal heating available to it, throwing out material several times a year on nothing but the weak sunlight of Jupiter's neighborhood and whatever chemical energy is stored in its own ice. There is another way to see why the timing question is hard. A conventional comet's activity is easy to model because it is driven by an external clock. The comet approaches the sun, gets hotter, and outgasses more. The heating is predictable, so the activity is roughly predictable. Strip that clock away, and you are left with an object whose eruptions are governed entirely by its internal state. How much volatile ice is buried where, how thick and how strong the crust is over each pocket, how far the crystallization front has advanced, how much heat the last eruption left behind. None of those quantities can be measured from 3/4 billion kilometers away. We are trying to predict the behavior of a pressure vessel whose interior we have never seen. Nobody can predict the next one. That is not for want of watching. 29P is among the most consistently monitored objects in the sky, and the monitoring is done largely by amateur astronomers, because catching an outburst requires observing on most clear nights over years, which is not how professional telescope time is allocated. A network of people with modest instruments has been tracking this comet's brightness for decades, and their light curves are the primary dataset. No model built on them reproduces the outburst statistics. The historical record adds a little weight to the puzzle. Arnold Schwarzmann and Arno Arthur Wachmann found the object at Hamburg Observatory in November of 1927, and for a long time it was catalogued simply as an unusually distant comet. Its outbursts were noted throughout the 20th century, sometimes bright enough to be picked up by visual observers, and the record of them is patchy in exactly the way you would expect from a phenomenon that requires someone to be looking on the right night. Modern automated surveys have improved the coverage substantially, but they have not revealed a hidden regularity. If anything, better coverage has shown that the events are more varied than the older record suggested. Different rise times, different total energies, different durations of the elevated state afterwards. A mission concept has been proposed to fly to 29P and observe an eruption from close range. It has not been selected, which means that for the foreseeable future, an object the size of a large city will keep erupting on a schedule nobody can anticipate. In a part of the solar system, our spacecraft cross regularly, watched mostly by people in their gardens. There is one more reason this object earns its place on a list about things we cannot explain. Centaurs are the pathway by which Kuiper Belt objects become the comets we see in the inner solar system, and what happens to them during that passage determines what a comet looks like by the time it reaches us. 29P is the best observed example of that transformation in progress. If we cannot account for the behavior of the clearest specimen we have, then our picture of how every short-period comet was prepared for its arrival is built on a step we do not understand. That is a body nobody has visited. The next item is one of the most studied moons in the solar system, with a spacecraft already on its way there. Number 10. The plumes that will not appear twice. Europa is slightly smaller than our moon, and almost certainly holds a global ocean of salt water beneath its ice. The evidence is strong and comes from several directions. The surface is young and nearly craterless, meaning it is being resurfaced. It is cracked in patterns that match tidal flexing of a shell floating on liquid, and Galileo's magnetometer detected an induced magnetic field, which requires a conducting layer near the surface, most plausibly a salty ocean. Estimates put the ice at 15 to 25 kilometers thick, with an ocean beneath it containing perhaps twice the water of every ocean on Earth combined. The single most valuable thing that could happen at Europa is a plume. A plume is a jet of ocean water venting through a crack in the ice into space. It matters because it turns an impossible problem into an easy one. Sampling an ocean under 20 kilometers of ice would require drilling technology that does not exist, delivered to a moon 500 million miles away, operating in an environment that would kill a human being in minutes. Sampling a plume requires flying through it. We know this works because it has already been done. Enceladus, a small moon of Saturn, vents continuously from fractures near its south pole at hundreds of kilograms per second, feeding a ring around the planet. Cassini flew through that plume repeatedly, and as a result we know the salinity of Enceladus's ocean, the presence of silica grains implying hot water at the rock interface, the presence of molecular hydrogen implying an available energy source, and the presence of phosphates and hydrogen cyanide. We know more about the chemistry of a moon 500 kilometers across than about a moon nearly the size of our own. So Europa has been watched hard. In 2012, Hubble's ultraviolet spectrograph recorded emission from hydrogen and oxygen above Europa's south polar region. That combination is the signature of water vapor being broken apart by radiation, and the geometry suggested vapor rising roughly 200 kilometers. In 2014 and again in 2016, a different team used a completely different method, watching Europa pass in front of Jupiter's bright disk and looking for silhouettes at the limb. They reported finger-like projections in the same general region. In 2017, another candidate appeared, apparently coincident with a warm spot that Galileo's infrared instrument had recorded 2 decades earlier. And a reanalysis of Galileo magnetometer and plasma wave data from a 1997 flyby found a signature consistent with the spacecraft having flown straight through a plume without anyone realizing it at the time. Then the detections stopped being reproducible. Infrared observations with SOFIA, the airborne observatory that flew a telescope in the side of a modified jet, published in 2019, found nothing. Ground-based observations with Keck found nothing on most nights, and something on one. And in 2023, the James Webb Space Telescope observed Europa with instruments sensitive enough to detect water vapor output far below the rates the earlier detections implied. It found none. The same observations produced a genuinely important result about the Moon: carbon dioxide on the surface, concentrated in a young, broken region called Tara Regio, and isotopically consistent with having come from inside rather than being delivered by impacts. That is direct evidence that material from the ocean reaches the surface. But the plumes were not there. The team was careful about what the non-detection meant, and their caution is correct. It does not rule out plumes. It rules out continuous plumes above a certain output. If the venting is episodic, tied to the tidal stress cycle as Europa moves through its slightly elliptical 3.5-day orbit, opening and closing cracks in the shell, then most observations will catch nothing, and that was the original prediction. Which puts the question in an awkward position. An intermittent phenomenon that appears in some observations and not in others is exactly what a genuine episodic plume looks like. It is also exactly what a series of marginal detections at the edge of instrument sensitivity looks like. From a distance, those two situations are difficult to tell apart. There is an underlying uncertainty that makes the whole question harder, and it is one of the more surprising gaps in what we know about a well-studied world. The thickness of Europa's ice shell is not settled. Estimates range from a few kilometers to more than 30, and the two ends of that range imply completely different moons. A thin shell flexes readily, cracks open all the way through, and lets ocean water reach the surface without much difficulty, in which case plumes should be common and the detections are probably real. A thick shell is rigid, and any liquid rising through it would freeze long before reaching the top, in which case plumes are nearly impossible and the detections are probably artifacts. The plume question and the shell question are entangled, and neither can be used to settle the other. The tidal cycle deserves a sentence of its own, because it is the engine behind everything here. Europa is locked in a resonance with Io and Ganymede, which keeps its orbit slightly elliptical instead of letting it circularize. That ellipticity means the tidal bulge raised by Jupiter shifts back and forth across the Moon as it orbits, flexing the shell twice per orbit. The flexing generates heat, which is what keeps the ocean liquid at a distance where it should be frozen solid. It also opens and closes fractures on a predictable schedule, which is why, if plumes exist, they should be periodic rather than random, and why observers have specifically looked at the orbital phase when the stress is highest. The specific difficulty is that both the ultraviolet detections and the transit detections require subtracting large backgrounds: Jupiter's own emission, Europa's reflected sunlight, the instrument's response function. Independent groups, re-reducing the same Hubble data, have disagreed about whether the signal survives careful treatment. That is not an accusation against anyone. It is a description of how hard the measurement is. Modeling has added a further complication. Work published on in situ detection found that flying a spacecraft through a weak plume may not deliver enough material to the instruments to identify it. The plume that would be easiest to see from Earth is the one big enough to have already been seen. The plume that is actually there, if it is there, may be small enough to be missed even by a spacecraft passing through it. This one, at least, has a date attached. Europa Clipper launched in October of 2024. It is the largest planetary spacecraft NASA has built, with solar arrays spanning more than 30 meters, an unavoidable consequence of working at Jupiter, which receives about 4% of the sunlight Earth does. It will not orbit Europa, because the radiation environment there would deliver a lethal human dose in minutes and would destroy electronics within weeks. Instead, it orbits Jupiter and makes repeated close passes, dozens of them, ducking in and out. It carries a mass spectrometer and a dust analyzer designed specifically to sample plume material. JUICE, the European mission launched in 2023, arrives in the same window with complementary instruments. Within about a decade, this will be settled. Until then, the most consequential question about the most promising place for life beyond Earth rests on a handful of detections that have refused to repeat. It is worth remembering how Galileo ended, because it bears on why the plume question was not settled long ago. The spacecraft made 11 close passes of Europa in the 1990s, with instruments that were state-of-the-art when it launched in 1989 and increasingly dated by the time it arrived. Its main antenna never fully unfurled, which cut its data rate to a small fraction of what was planned and forced the team to choose ruthlessly what to send home. In 2003, low on fuel and with no way to guarantee it would not eventually strike Europa and contaminate it, controllers deliberately steered it into Jupiter's atmosphere. The plume signature found in its archived magnetometer data was identified 15 years after the spacecraft had been destroyed. Europa's answer is coming, and a spacecraft is already in flight to fetch it. The next item is at a planet where several missions are working right now, and no answer is coming at all. Number 9. The storms that swallow a planet. Mars has dust storms constantly. That much is ordinary. Every Martian year, storms lift dust out of particular basins, run for a few weeks, and settle. They are watched from orbit, catalogued, and largely unremarkable. Then, on no schedule anyone can predict, a regional storm fails to settle. Instead, it grows, and keeps growing, until it covers the entire planet. These are called planet-encircling dust events, and they occur roughly once every 3 or 4 Martian years, which is another way of saying unpredictably, since the observed intervals have ranged from 2 to more than 10. The storm of 2018 is the best documented event of its kind. It was first noticed on the 31st of May 2018 as a regional disturbance in Acidalia Planitia. Within about 2 weeks, it had wrapped around the planet. To understand what that does to conditions on the ground, you need one number. Atmospheric opacity is measured as an optical depth, and each unit of optical depth cuts the light reaching the surface by roughly a factor of 3. Normal Martian conditions run around 0.5. During the 2018 storm, the optical depth measured at Gale Crater rose above 11. That corresponds to direct sunlight being attenuated by a factor of tens of thousands. The sun became invisible. What light remained was scattered and reddened, and there was almost none of it. Curiosity, which sits in Gale Crater, is powered by the heat of decaying plutonium. It kept working. It used its navigation cameras to measure the size and shape of the dust particles, which turn out to be roughly 1 to 2 micrometers across and extremely good at absorbing sunlight. That absorption is why the atmosphere warms by tens of degrees during a storm, while the surface beneath it gets colder. Opportunity was on the other side of the planet, at Meridiani Planum, and Opportunity ran on sunlight. It had landed in January of 2004 for a mission designed to last 90 days. It had been working for 14.5 years. It had driven more than 45 kilometers across the surface, further than any vehicle had traveled on another world. It had outlived its twin, Spirit, by 8 years. It had found the mineral evidence that Meridiani had once been soaked in water. Its wheels had worn, one of them had seized, its heaters had failed, and it had kept going. The rover was designed to weather dust storms by entering a low-power state, waking periodically to check whether the sky had cleared. It sent its last transmission on the 10th of June 2018, reporting a power level too low to sustain operations. Picture the last few days. The sky at Meridiani goes from butterscotch, which is its normal color, to something browner, and then to something closer to unlit. The panels, already carrying years of accumulated dust, receive a fraction of their rated power. The batteries drain to keep the internal electronics from freezing in the night. There is no drama in it, and nothing breaks. A machine that had been working for 14 years simply runs out of light, in silence, several 100 million kilometers from anyone. The team listened for 8 months. More than 1,000 recovery commands were transmitted. The mission was declared complete in February of 2019. The cause of death was a storm of a kind that begins many times each Martian year and almost always stops. The growth mechanism is understood in outline, and it is a feedback loop. Lifted dust absorbs sunlight, which warms the surrounding air. Warmer air strengthens the winds. Stronger winds lift more dust. Once the loop is running strongly enough, it sustains itself. Orbital observations during global storms have revealed a further piece of machinery: dust towers. These are concentrated plumes of dust that reach 60 to 80 kilometers in altitude, far above the normal dust layer. They appear to act as elevators, injecting material into the upper atmosphere, where the global circulation can carry it around the planet. They also appear to lift water vapor to altitudes where it can be broken apart by ultraviolet light and lost to space, which connects these storms directly to the long-term drying of Mars. There is a persistent misconception about these storms that is worth correcting, because it runs the wrong way. Martian dust storms are often described as violent, with winds quoted at 100 kilometers per hour or more, and those wind speeds are accurate. But the Martian atmosphere is about 1% as dense as Earth's at the surface. Force depends on density as well as speed, and 100 kilometer per hour wind in air that thin carries roughly the push of a gentle breeze here. It would not knock a person over. It would not topple a lander. What it does is lift dust, because the particles are extremely fine and the gravity is a third of Earth's, and once lifted, they stay suspended for months. The danger is not mechanical, it is optical. That distinction is exactly why the storms are lethal to solar-powered hardware and merely inconvenient to everything else. It also explains a second, slower problem. InSight, the stationary lander that measured Marsquakes from 2018 onward, was not killed by a global storm at all. It died gradually, as ordinary suspended dust settled onto its panels year after year, cutting the power available until there was not enough to run the seismometer. The mission ended in December of 2022. 2 spacecraft, 2 different dust problems, the same outcome. What is not understood is why any particular storm crosses the threshold. Dozens of regional storms begin each Martian year from what appear to be equivalent starting conditions. Almost all of them stop. There is no reliable precursor that distinguishes the ones that will not. Global storms occur during southern spring and summer, when Mars is nearest the Sun and the atmosphere is warmest. But most storms in that season also fail to go global, so seasonality narrows the window without predicting the event. Attempts to find a correlation with how much dust is available on the surface, with the sublimation of the polar caps, with the thermal structure of the atmosphere, or with whether a storm occurred the previous year, have not produced a working predictor. Modeling published in 2024 suggests that unusually warm, clear days beforehand may make a global storm more likely, which is a statistical tendency rather than a mechanism. The scientists who work on this say so directly. The variability has not been explained. There is a neat historical bookend. Mariner 9 arrived at Mars in November of 1971, the first spacecraft ever to orbit another planet, and found a featureless orange ball. A global dust storm was in progress. The mission had to wait, photographing nothing, for weeks. When the dust finally settled, the first features to emerge from the haze were 4 dark spots near the equator, which turned out to be the summits of the largest volcanoes in the solar system, projecting above the storm. The planet's greatest landmarks were revealed by the same phenomenon that had hidden everything else. Global storms have been recognized from Earth for a long time. Telescopic observers recorded planet-wide yellow clouds in the 1890s, well before anyone knew what the Martian surface was made of, and the record of them stretches through the 20th century in the notebooks of visual observers. That long baseline is part of why the irregularity is so well established. This is not a phenomenon we have only sampled for a few decades from orbit. It has been watched, at some level of detail, for more than a century, and no periodicity has emerged. The practical stakes have not changed since. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. That is a storm we can at least watch happen. The next item at the same planet is a gas that one instrument measures and another cannot find. Number 8. The gas that is there and is not there. Methane on Mars would matter for one specific reason. It should not last. Solar ultraviolet light breaks methane apart. On Mars, with a thin atmosphere and no ozone layer to speak of, the destruction timescale is a few hundred years. Against the age of the planet, a few hundred years is nothing at all. So any methane present in the Martian atmosphere today was released recently, in geological terms, and something is currently making it. That is what gives the question its weight. On Earth, the overwhelming majority of atmospheric methane is produced by living things, by microbes in wetlands, in soil, and in the guts of animals. On Mars, the possible sources are 3, and all of them are interesting. The first is biology, and it needs no elaboration. The second is water reacting with rock. When water contacts olivine-rich minerals at depth, it produces serpentine and hydrogen through a process called serpentinization, and the hydrogen can then combine with carbon to form methane. This requires liquid water underground, and it can proceed slowly at low temperatures, which means a subsurface aquifer several kilometers down could be quietly producing methane with no biology involved and no visible expression at the surface other than a seep. The third is storage. Methane molecules can be caged inside a lattice of water ice, forming what is called a clathrate. Clathrates are stable at Martian subsurface conditions, which means gas produced billions of years ago could still be locked away, released whenever the ice is disturbed. Any of the three would be a significant result about a planet next door. So the measurement has been attempted repeatedly, and this is where it becomes strange. Curiosity carries an instrument suite called Sample Analysis at Mars, and within it, a tunable laser spectrometer. The technique is direct. Shine a laser tuned precisely to a wavelength, methane absorbs, pass the beam through a chamber of Martian air, and measure how much light is missing. The instrument can also run in an enrichment mode that concentrates the sample first, improving sensitivity by a factor of around 25. Curiosity has been making these measurements in Gale crater since 2012. It finds a background methane level of around 0.4 parts per billion. That level varies seasonally by roughly a factor of 3. And on a number of occasions, it has recorded spikes reaching about 21 parts per billion, dozens of times the background. The measurements have been repeated over more than a decade by a working instrument, operated carefully. The ExoMars Trace Gas Orbiter arrived at Mars in 2016 and began science operations in 2018. It was built for this. Its spectrometers were designed specifically to detect trace gases at parts per trillion sensitivity, between 10 and 100 times better than anything that had gone before. It has surveyed the entire planet repeatedly for years. It has detected no methane at all. Its upper limit sits around 0.05 parts per billion, which is roughly 10 times below the background level that Curiosity reports from the surface. Two well-built instruments, both working correctly, both operated by careful teams who have checked their own results exhaustively. And they disagree about whether a gas exists in the atmosphere of a planet where we currently have several orbiters and multiple vehicles on the ground. It is worth knowing that this argument is older than either spacecraft. The first claimed detections of Martian methane came in 2003 and 2004, from ground-based telescopes and from the European Mars Express orbiter, at levels around 10 parts per billion. They were disputed almost immediately, and for a good reason. Earth's own atmosphere contains far more methane than the amount being sought on Mars, so a ground-based measurement has to subtract an enormous local signal to reveal a tiny distant one. Mars Express was above that problem, but working at the limit of its instrument. Neither claim was ever confirmed, and neither was ever cleanly retracted. Curiosity was supposed to end the argument by measuring from the surface, where there is no terrestrial atmosphere in the way. Instead, it began a new one. There is also a point in the orbiter's favor that should not be skipped, because it rules out the simplest dismissal. The Trace Gas Orbiter is not an instrument that fails to see things. It made the first detection of hydrogen chloride in the Martian atmosphere, a gas nobody had expected to find there, at concentrations of a few parts per billion. It has mapped water vapor and its isotopes through the atmospheric column and watched them respond to dust storms. It is demonstrably capable of finding trace species at exactly the levels in question. It simply does not find this one. The most discussed reconciliation involves geometry and time of day, and it is elegant. The trace gas orbiter uses a technique called solar occultation. It watches the sun set or rise through the Martian atmosphere and measures which wavelengths are absorbed along that path. Looking edge-on through the atmosphere gives an enormous path length, which is where the extraordinary sensitivity comes from. But it also means the instrument samples the atmosphere from about 5 kilometers altitude upward, and only at dawn and dusk. Curiosity samples at the surface, and its most confident detections come at night. Work at NASA's Goddard Space Flight Center showed why that combination matters. Martian nights produce a strongly stratified boundary layer. With no sunlight, there is no convection, and the air near the ground stops mixing with the air above it. Any methane seeping out of the ground accumulates in a thin layer right at the surface, exactly where the rover sits. Then the sun rises, the ground warms, convection starts, and that thin layer is stirred through several kilometers of atmosphere, diluting the concentration below the orbiter's detection threshold at precisely the time the orbiter is looking. It is a good explanation. It is also not sufficient, and the reason is arithmetic. Methane persists for centuries. Even a small, diluted seep should therefore accumulate globally over time, building up until the whole atmosphere carries a detectable background. Estimates suggest the levels Curiosity measures would reach orbiter-detectable concentrations in about 20 years, if nothing removed them. The orbiter does not see it. So the explanation does not close the problem. It forces a second, separate unknown. There must be a removal process operating near the Martian surface, hundreds of times faster than ultraviolet photochemistry, that nobody has identified. Candidates have been proposed. Oxidation on the surfaces of dust grains. Electrostatic discharge in dust devils, which are common and carry substantial charge. Heterogeneous chemistry on perchlorate salts, which are abundant in Martian soil. None of these has been demonstrated in the laboratory at anything close to the required rate. There is a third layer to this, and it undercuts the ground beneath the whole discussion. Some statistical analyses of the Curiosity dataset have concluded that there is no significant seasonal cycle at all, that the apparent pattern is an artifact of when the measurements happened to be taken and how the instrument was operated between them. Other analyses find the seasonal signal robust. That argument has not been settled either. And there is a further deflating possibility. Modeling has shown that the observations can be matched if the source is very small and located extremely close to the rover, for instance, somewhere in the northwestern rim of Gale Crater. That would make Curiosity's methane a local phenomenon rather than a planetary one. It would also raise an obvious question. Why did the rover happen to land on top of the only active vent anyone has found? More recent work has proposed that the seeps are governed by subsurface salt crusts that seal and unseal as temperature and pressure change through the day and the year, releasing gas in bursts. And, more awkwardly, that some of the methane the rover detects may be released by the rover itself, by the weight of its wheels crushing surface crust as it drives. That possibility is mundane, unflattering, and has not been ruled out. The stakes reach beyond methane. If there really is an unidentified process at the Martian surface, destroying organic molecules hundreds of times faster than sunlight alone, then it is not selective. It would be destroying the other organics too, the complex carbon compounds that any search for ancient life would need to find preserved in rock. Curiosity has now driven more than 35 kilometers across Gale Crater and climbed over 800 meters up the slopes of Mount Sharp, sampling progressively younger layers of sediment as it goes, and every organic detection it has made has to be interpreted against the possibility that most of what was originally there has already been erased by a mechanism nobody can name. Rosalind Franklin, The European rover carrying a 2-meter drill was designed with this problem in mind. The drill depth was chosen specifically to reach below the oxidizing surface layer, where organic molecules, and any evidence of what is producing or destroying methane, might survive. Here is the plain summary. After more than a decade of work, using the most capable instruments ever sent to another planet, we cannot say with confidence whether Mars is releasing methane. If it is, we cannot say what makes it. And if the surface measurements are right, we cannot say what destroys it, because whatever does so is operating hundreds of times faster than the chemistry we know about. This is another answer that was checked and failed. The night layer explanation is careful, well-motivated, supported by atmospheric modeling, and it leaves behind a hole in the chemistry that is larger than the hole it filled. Mars is a difficult planet to instrument, and there is some excuse in that. The next item is about the planet nearest to us in size, and it concerns the air itself. Number 7. The air that outruns the planet. Venus turns very slowly, and it turns the wrong way. A single rotation takes 243 Earth days in the opposite direction to almost everything else in the solar system. A point on the Venusian equator is carried around at about 6.5 kilometers per hour. That is slower than a person walking briskly. If you stood on the surface, setting aside that the surface is hot enough to melt lead and the pressure is what you would feel 900 meters underwater, the ground beneath you would be moving at a pace you could outstrip on foot. The atmosphere above that surface, at the cloud tops roughly 70 kilometers up, circles the entire planet once every 4 Earth days. The winds there run at around 360 kilometers per hour. The air is moving about 60 times faster than the planet it sits on. This is called superrotation, and the discovery has a good story attached. In the late 1950s and early 60s, a French amateur astronomer named Charles Boyer photographed Venus in ultraviolet light, where the otherwise blank disk shows dark markings. He tracked those markings and found they returned to the same position every 4 days. Almost nobody believed him. A 4-day atmospheric circulation on a planet that takes 8 months to rotate was, at the time, absurd. Spacecraft confirmed it, and the 4-day period has been measured many times since. The difficulty is a conservation problem, and it is worth setting out carefully because it is what makes this a genuine unsolved question rather than a curiosity. An atmosphere gets its rotation from the surface it rests on, transmitted upward by friction. That same friction should, over time, drag the atmosphere back toward the surface's speed. On Venus, the atmosphere is not merely faster than the surface. It holds a store of angular momentum many times larger than its fair share, and it has held that store for as long as we have been able to measure it. Something must be continuously transporting angular momentum from the lower atmosphere upward and from the mid-latitudes toward the equator, against the drag and against the overturning circulation that would otherwise drain it away. Identify that transport, and you have solved the problem. The classical answer was proposed in the 1970s and is named for Peter Girash, Werner Suomi's colleagues, and later Richard Rousseau and Gareth Williams. It works like this. A slow pole-to-equator overturning circulation carries angular momentum upward, and large-scale horizontal eddies, planetary-scale turbulence, carry it back toward the equator, closing a loop that sustains the fast equatorial winds. The mechanism is sound in principle. Whether it is what Venus actually does was untestable for 40 years, because testing it requires measuring the actual wind field precisely enough to compute where angular momentum is flowing and how much. Akatsuki provided that. And the story of how it got there is the reason this measurement exists at all. Akatsuki is a Japanese orbiter launched in 2010. In December of that year, it arrived at Venus and fired its main engine for orbit insertion. The engine failed partway through the burn. A corroded valve had starved it of oxidizer, and the nozzle broke apart. The spacecraft sailed past the planet and fell into an orbit around the Sun instead. That is normally the end of a mission. The team did not accept that it was. Over the following 5 years, they worked out whether the spacecraft could be captured using nothing but its small attitude control thrusters, which are intended for pointing and had never been designed to perform an orbital insertion. They had to wait for Venus and the spacecraft to come back into alignment. They had to dump the remaining oxidizer to rebalance the vehicle, and they had to be right the first time. In December of 2015, 5 years late, using 4 thrusters never meant for the job, Akatsuki entered orbit around Venus. It remains the only planetary orbit insertion ever achieved that way. Its ultraviolet imager then tracked cloud features across the disk at high cadence for years, building wind maps detailed enough to separate the contributions of different kinds of atmospheric wave. In 2020, Takeshi Horinuchi and colleagues published the analysis. The mechanism at the cloud top is thermal tides. The Sun heats the day side of the cloud deck, and because the planet rotates slowly, the heating pattern is essentially fixed relative to the Sun. That excites atmospheric waves which propagate and deposit momentum where they break, supplying angular momentum toward the equator and sustaining the superrotation at that level against the circulation that would drain it. And there was a second finding that mattered as much as the first. The other waves and the large-scale horizontal turbulence were found to be acting in the opposite direction, weakly decelerating the flow. In the classical picture, those eddies were the accelerating agent. Measured, they turned out to have the wrong sign. So the cloud top budget is now established, and the mechanism that had been the standard explanation for 4 decades is not what is happening there. That is real progress, and it does not close the question. The superrotation extends from roughly 10 kilometers altitude to above 80. Akatsuki measured the top of that column. Below the clouds, where the overwhelming majority of the atmosphere's mass sits, the angular momentum budget is entirely unmeasured because no orbiter can see through the cloud deck to track motion at those depths. Simulation work has continued to publish revised balances for the middle and upper atmosphere, with different conclusions about which waves dominate. And the origin question is untouched. Knowing what sustains a super-rotating state does not tell you how one gets established from rest, or whether Venus's slow backwards rotation is a cause of the superrotation or a consequence of it. There is a plausible argument that the atmosphere itself, carrying so much angular momentum, has torqued the planet's spin over billions of years, which would make this a case of the air having reshaped the world beneath it. The difficulty of working at Venus is worth stating plainly, because it explains why the deep atmosphere has never been measured. The Soviet Venera program put a series of landers on the surface between 1970 and 1982. And they were engineered as pressure vessels rather than spacecraft. Titanium shells, thermal ballast chilled before launch, everything built to buy minutes. Venera 7 survived 23 minutes. Venera 13 managed just over 2 hours and returned the only color photographs of the Venusian surface anyone has, showing flat plates of rock under an orange sky. Nothing has landed since. A probe descending through the cloud deck spends perhaps an hour in the region where the winds are strongest, and it is falling the whole time, which is not how you build a wind record. There is a further sign that our understanding is incomplete, and it is embarrassingly basic. Measurements of Venus's rotation period, taken by different missions across several decades, do not agree with one another. The discrepancies amount to several minutes in the length of a Venusian day. Several explanations have been offered, and the leading one is the atmosphere itself. A body of air carrying that much angular momentum exerts a real torque on the solid planet, and the exchange can measurably change the length of the day over the span of a few decades. We are, in other words, unable to state precisely how fast Venus turns, because the air is pushing on it, and we cannot fully account for the push. There is one more reason not to file this under planetary trivia. Titan superrotates as well, at a comparable ratio, and Titan is a completely different object, a small, frigid moon with a nitrogen atmosphere and no sunlight to speak of. Earth's own tropical stratosphere superrotates weakly, and the mechanism there is also wave-driven. Whatever is going on appears to be a general property of slowly rotating bodies with substantial atmospheres, which makes it a fundamental question in atmospheric physics rather than a peculiarity of one planet. It is a strange thing to have a planet in the same size class as our own, close enough that its atmosphere can be studied from a backyard telescope in the right filter, and to be unable to write down where its weather gets its energy from. The equations are not exotic. They are the same fluid dynamics that govern the jet stream. The system is simply large, slow, hot, opaque, and almost entirely out of reach. The winds on Venus are at least visible. What makes them visible is the next item on this list, and after 100 years, nobody knows what it is. Number 6. The substance nobody has named. Photograph Venus in visible light, and you get a blank white ball. There is nothing to see. The cloud deck is uniform, brilliant, and completely featureless, which is why, for centuries, telescopic observers could not even establish how fast the planet rotated. It reflects about 3/4 of the sunlight that falls on it and gives away nothing. Photograph the same planet in ultraviolet and it transforms. Dark bands sweep across the disk in broad curving stripes, tilted and sheared, carried around by the 4-day super-rotating flow. Mottled patches appear and dissolve. There is structure and motion and something recognizable as weather. Those markings were first captured photographically in the 1920s. Frank Ross, working at Mount Wilson in 1927, used newly available ultraviolet-sensitive plates and found the features that every mission since has seen. They are how Charles Boyer measured the superrotation. In a real sense, they are the only visible weather on the planet, and everything we know about how the Venusian atmosphere moves has been tracked using them. They are produced by something in the clouds that absorbs light strongly between about 300 and 500 nanometers, the near ultraviolet and the blue end of the visible. Nobody knows what it is. Start with the part that is settled, because it makes the unsettled part sharper. Below about 320 nanometers, the absorption is caused by sulfur dioxide. That is understood, measured, and not in dispute. Sulfur dioxide is abundant in the Venusian atmosphere, and its absorption spectrum is well characterized in the laboratory. Above 320 nanometers, out to about 500, there is a second absorber, and it has been unidentified for 100 years. It is referred to in the literature simply as the unknown ultraviolet absorber, which is an unusual thing for a scientific field to have to keep writing down for a century. Now the number that makes this belong on this list. That unknown substance absorbs roughly half of all the solar energy Venus takes in. Not half of the ultraviolet. Half of the total. Because the clouds are so reflective, most of the sunlight arriving at Venus is turned straight back into space, and a large fraction of what does get absorbed is absorbed by this compound in a layer a few tens of kilometers thick near the cloud tops. That energy deposition drives the atmospheric circulation. It is a first-order term in the energy budget of an entire planet, and it is unattributed. It is worth putting that quantity in a familiar frame. Venus receives roughly twice the sunlight per square meter that Earth does, being closer in. Multiply that by the planet's cross-section, subtract the enormous fraction reflected away by the clouds, and what remains is still an energy flow comparable to everything the Earth receives from the Sun. A substantial share of that is captured by one unidentified substance and deposited into a shell of atmosphere a few tens of kilometers thick. Every model of Venusian climate, every simulation of its circulation, every attempt to reconstruct how the planet became what it is, has to include a heating term whose source is written into the equations as an empirical fit rather than a chemical. More than 20 candidate compounds have been proposed over the decades. Elemental sulfur in various molecular forms. Disulfur monoxide. The sulfur monoxide dimer, known as OSO. Ferric chloride, argued for and against repeatedly since the 1970s. Ammonium pyrosulfate. Various chlorine compounds. Nitrosyl sulfuric acid. And, proposed seriously, defended repeatedly, never established, light-absorbing microorganisms living in the cloud droplets, on the grounds that the cloud layer is the one place on Venus where temperature and pressure are not immediately lethal. The difficulty is not a shortage of spectra, it is the environment. Any candidate has to survive suspended in droplets of 75 to 98% sulfuric acid at those temperatures under that ultraviolet flux for long enough to be present in the required quantity. And it has to reproduce the exact shape of the absorption curve, not merely absorb somewhere in the right region. Most candidates fail one of those two tests. Elemental sulfur has approximately the right spectral shape, but is not stable in the necessary form. OSO fits the shape reasonably well, but the amount that can be produced falls short of what is needed. The most substantial recent progress came from a group at Cambridge who took the laboratory approach seriously. Rather than proposing a compound and comparing published spectra, they synthesized iron-bearing sulfate minerals under conditions simulating Venusian cloud chemistry and measured their absorption directly. They found that a combination of two minerals reproduces the observed feature well: rhomboclase and acid ferric sulfate, dissolved in sulfuric acid at different concentrations. The best fit was roughly equal contributions from about 1% rhomboclase in 74% acid and about 1.25% acid ferric sulfate in 84% acid, which itself implies droplets of differing acid strength coexisting in the cloud deck. The fit was compared against measurements from Akatsuki, from Bepi Colombo as it flew past on its way to Mercury, and from ground-based observations. It is the best chemical match anyone has obtained under realistic conditions. It is also a laboratory result matched to a remote sensing curve, which is not the same as a detection. No instrument has ever measured the composition of a Venusian cloud droplet. And the field has not converged. Modeling published in 2025 argued that the bulk absorbance of the cloud liquid is also consistent with organic absorbers present at high concentration, which keeps the biological hypothesis formally alive without supporting it. That is roughly where things stand. A century of proposals, one strong recent laboratory candidate, no measurement in place, and a compound governing half the energy Venus absorbs still without a name. There is a further wrinkle that deserves attention. The strength of the ultraviolet markings varies. Over decades, the contrast between the dark bands and the bright background has changed by up to a factor of 2, which means the overall reflectivity of the planet has measurably changed within the era of spacecraft observation. Nobody knows what drives that either. And because the absorber deposits energy at the cloud tops rather than the surface, a change in its abundance directly changes the atmospheric circulation. The two unsolved problems, what makes the winds and what makes the markings, are physically connected. Solve one and you constrain the other. It also helps to know where the clouds sit, because the geography of the problem is narrower than it sounds. The sulfuric acid cloud deck occupies a band from roughly 50 to 70 kilometers above the surface. Below about 30 kilometers, the droplets evaporate entirely in the rising heat, so the clouds are a thin, chemically isolated layer suspended in a very deep atmosphere, with hundreds of kilometers of clear, hot gas beneath them. The absorber lives near the top of that layer. It is not distributed through the planet. It is concentrated in a shell, and that shell is where all the visible structure comes from. The measurement that would settle it requires being inside the clouds. A droplet on Venus is roughly 1 to a few micrometers across, and it would evaporate or react on the way down, so a probe would have to capture and analyze them in flight, rather than bringing anything back. Several missions in development would do exactly that, including atmospheric probes, new orbiters, and a proposed balloon platform designed to float within the cloud deck for weeks. Until one of them flies, the darkest markings on the nearest planet to us remain anonymous. They have been photographed for 99 years. There is a particular quality to a mystery of this shape that is worth naming before we move on. Most of the items on this list are things we cannot explain because we cannot reach them, or because they happen too rarely, or because the signal is at the edge of what an instrument can resolve. This one is none of those. The signal is enormous and has been recorded continuously since before the invention of the transistor. The absorber is not hiding at the limit of detection. It is the single most conspicuous feature the planet has when photographed at the right wavelength. We have taken its picture tens of thousands of times. We simply cannot say what we have been photographing. Venus is at least shrouded, and there is some defense in that. The next item is on a surface with no atmosphere at all, that 12 people have walked on. Number 5. The pale ribbons painted on the moon. Scattered across the moon, there are bright markings that look painted on. That is not a figure of speech. They swirl and loop across the surface in sinuous bands, curling back on themselves, sometimes tens of kilometers wide and hundreds long. They cross craters without deflecting. They run over ridges and down into plains without changing shape. And they cast no shadow at any angle of illumination because they have no relief whatsoever. Whatever they are not landforms. They are a difference in brightness, lying on top of the landscape, indifferent to it. The best known is Rhina Gamma, an oval roughly 70 kilometers long in Oceanus Procellarum on the near side. It is bright enough to be seen in a modest backyard telescope, and it was catalogued centuries ago. Early selenographers marked it as a crater because bright features on the moon are usually craters, and it took much better imaging to establish that there is nothing there at all in the topographic sense. To understand why they matter, you need to know why the moon is dark. The lunar surface has no atmosphere and no magnetic field to shield it. The solar wind, a continuous stream of protons and electrons from the sun, strikes the regolith directly. So do micrometeorites, constantly, at high speed. Between them, these two processes chemically alter the surface layer. They reduce iron in the minerals to tiny grains of metallic iron, and those grains darken and redden the soil. This is called space weathering, and it operates on every airless body. It takes somewhere between 100 million and 1 billion years to run its course. Fresh material, excavated by a recent impact, appears bright. Over time, it fades into the background. The swirls are bright because they have not weathered. Something has been shielding them. That something is magnetic, and this part is established rather than speculative. Every lunar swirl sits on a magnetic anomaly, a patch of magnetized crust producing a local field strong enough to stand off the solar wind and form what is effectively a miniature magnetosphere, a few tens of kilometers across. Charged particles arriving from the sun are deflected around it. The ground underneath stays chemically fresh and stays bright. Orbital magnetometers carried by the Apollo 15 and 16 sub-satellites, by Lunar Prospector, and by the Japanese Kaguya mission have mapped the correspondence in detail. The darker lanes that run between the bright swirls line up with the regions where the deflected particles are concentrated and land more heavily. The pattern is consistent. Stand inside one, and the strangeness becomes physical. The ground beneath your boots is noticeably paler than the ground a few hundred meters away, and there is no step, no ridge, no change in slope where the boundary falls. You could walk across the edge of the swirl without your feet registering anything at all. Overhead, there is nothing to see. But an invisible magnetic structure a few tens of kilometers wide is standing over this patch of ground, and only this patch, holding back a wind that has been steadily darkening every other square meter of the moon for 4 billion years. There is no source visible anywhere. The moon has no magnetic field. This one place does. That is the actual mystery. Not the brightness, which is explained. The magnetism. The moon has no global magnetic field today, and no active core dynamo generating one. It had one once. Apollo samples carry remnant magnetization locked in when they cooled, though exactly how strong that ancient field was, and for how long it ran, has been argued over for decades and remains contested. But the swirl anomalies are far stronger than the surrounding crust and sharply localized. There is no obvious reason a crust magnetized by a global dynamo should be patchy in this particular way, in these particular places. 3 explanations compete, and they genuinely compete. None has won. The first is comet impacts. A comet hitting the surface arrives with an ionized coma around it, a cloud of charged gas. That interaction with the surface, in the presence of any ambient field, could both scour and brighten the regolith and magnetize the material locally. Reiner Gamma's shape, a bright oval with a long trailing extension, has been read as exactly this kind of oblique cometary strike. The second is that the magnetism came first, and the swirl is a consequence. On this account, a body of iron-rich rock intruded beneath the surface long ago, a dike, a buried lava tube, or the melt sheet at the floor of an old impact crater, and cooled while the ancient dynamo was still running, locking in a strong local field. The bright swirl then developed slowly over billions of years as that field deflected the solar wind. Detailed magnetic modeling has shown that Reiner Gamma's field is well fitted by a uniformly magnetized elliptical disk buried beneath the surface, which is what the floor deposits of an oblique impact crater would look like. The third proposes that the brightness is not about shielding at all, but about sorting. Fine dust, lofted by micrometeorite impacts, carries electrostatic charge, and a local magnetic field would separate and deposit that dust preferentially, concentrating the brightest and finest material in particular patterns. There is real evidence for this. Polarimetric imaging of Reiner Gamma at large phase angles shows that the regolith there has genuinely unusual physical properties, different grain structure, not merely different chemistry. The sorting hypothesis predicts that. The others do not obviously require it. There are details that any successful explanation has to accommodate, and they pull in different directions. Swirls appear on both the near side and the far side. Several of the far side groups, including the one at Mare Ingeni and the anomaly near the crater Gerasimovich, sit almost exactly opposite large impact basins on the other hemisphere. That antipodal arrangement has been used to argue for a different mechanism again, that a giant impact generates a transient magnetic field as the vaporized plume expands, and that field is focused at the point directly opposite, magnetizing the crust there as it cools. It is an elegant idea, and it accounts for some swirls and not others. The swirls also do not care what kind of rock they sit on. Some are on the dark basaltic plains of the Maria, others on the pale highland terrain, and the phenomenon appears the same in both. So the effect is not a property of a particular material. And there is a useful comparison next door that makes the lunar case stranger rather than clearer. Mercury also has crustal magnetic anomalies. The Messenger spacecraft detected them, remnants of an ancient field locked into old terrain. Mercury has no swirls. Whatever combination of circumstances produces bright ribbons on the Moon apparently does not occur there. Why has this not been settled? Because all three mechanisms produce something that looks broadly correct from orbit, and the measurements that would distinguish them require being on the ground. You need the magnetic field strength at the surface, rather than 100 kilometers above it. You need the depth and shape of the source body. You need the composition and the physical grain structure of the bright material in place. A small lander and rover mission called Lunar Vertex is designed to do exactly that at Rhina Gamma, land inside the swirl, measure the field where it is strongest, and drive across the boundary between bright and dark ground while sampling both. There is a practical reason to want the answer beyond curiosity. Because swirl regions are shielded from the solar wind, the hydrogen implanted in their soil differs from the surroundings. Solar wind protons are one of the proposed sources of the water detected across the lunar surface, and a swirl is a natural control experiment. The same latitude, the same illumination, the same micrometeorite flux, but a fraction of the proton exposure. Comparing the two would help settle where lunar water comes from, which matters for anyone planning to use it. Until it does, the most conspicuous unexplained markings anywhere in the solar system remain roughly 150,000 square kilometers of decoration on a body that 12 people have walked on. The Moon is close. The next item is closer still. In one sense, it happens on the surface of the star that this entire system orbits. Number 4. The earthquakes that begin beneath the Sun. In 1972, a solar physicist named Charles Wolfe worked out that a sufficiently violent flare ought to send seismic waves through the Sun. Nobody saw one for 26 years. The Sun is not solid, but it carries sound. Its interior is a resonant cavity, and it rings continuously at millions of frequencies, driven by the churning of convection near the surface. That ringing is the basis of helioseismology, the discipline that reads the Sun's internal structure from the pattern of surface oscillations, in the same way a geologist reads the Earth's interior from the arrival times of earthquake waves. Helioseismology is how we know the depth of the convection zone, the rotation rate at different latitudes and depths, and the location of the tachocline where the interior's rigid rotation gives way to the surface's differential rotation. It works well. What Wolfe predicted was different, not the continuous background hum, but a single impulsive event. A localized disturbance that would spread outward as a distinct set of ripples. The first one was found in data from the SOHO spacecraft for a flare on the 9th of July, 1996, and reported by Alexander Kosovichev and Valentina Zharkova in 1998. The images were made in Doppler velocity, a map of how fast each patch of the solar surface is moving toward or away from the observer, and in those images the event is startlingly literal. A set of concentric circular ripples spreads outward from the flare site across the photosphere, exactly like the rings from a stone dropped into still water. They were named sunquakes. The ripples travel outward for tens of minutes, and they accelerate as they go, from perhaps 10 kilometers per second near the source to over 100 further out. That acceleration is not the waves speeding up in place. It is a consequence of how the waves travel. The disturbance dives into the interior, refracts through the steep density gradient there, and returns to the surface some distance away. Waves that dive deeper travel faster and surface further out. The visible expanding ring is a sequence of returning waves, each one having gone deeper than the last. By the time the ring has finished spreading, it covers an area many times the size of the Earth. The energy involved is very large. But energy is not the puzzle here. The puzzle is location. The obvious assumption was that a sunquake is a flare hitting the surface from above. A flare occurs in the corona, in the tenuous atmosphere above the photosphere, when a stressed magnetic field reconfigures itself and releases stored energy. Some of that energy goes into accelerating particles downward. When a beam of high-energy electrons and protons slams into the dense photosphere, it deposits its momentum abruptly, and that impulse could ring the sun. Alternatively, the sudden magnetic reorganization itself could press on the surface like a hand. That picture had trouble from the start. Only a small fraction of flares produce sunquakes, and the ones that do are not reliably the most energetic. Some quite modest flares produce strong, clean seismic ripples. Some enormous flares produce nothing detectable at all. Fewer than 1 in 10 large flares generates a sunquake, and the strongest sunquake on record did not come from one of the largest flares observed. Worse, in some events, the acoustic energy measured in the ripples appears to exceed what the downward directed particle beam could plausibly have delivered. It is worth pausing on how thin the layer we are talking about actually is. The photosphere, the visible surface of the sun, the layer that produces essentially all the light we see, is only a few hundred kilometers thick. Below it, the gas becomes opaque. Above it, transparent. On a body some 1.4 million kilometers across, that is a skin comparable in relative thickness to the skin on an apple. Everything we observe directly about the sun happens in or above that skin. Everything else is inferred, and helioseismology is the main tool for inferring it. Then, in 2020, the picture inverted. A team applied a technique called helioseismic holography to a sunquake associated with a moderate flare in July of 2011, recorded by the Solar Dynamics Observatory. The observatory images the entire solar disk in Doppler velocity every 45 seconds, which is what makes this kind of analysis possible at all. Helioseismic holography treats the surface wave field as a hologram and computationally focuses it backwards, running the propagation in reverse to locate where the waves originated, the acoustic equivalent of using a lens the wrong way round. The source was not at the surface. It was not above it either. It was roughly 1,100 kilometers below the photosphere. About 1 megameter down, well inside the convection zone, in gas roughly 10 times denser than the visible surface. That inverts the causal picture entirely. A flare occurring in the atmosphere is somehow triggering an acoustic source buried 1,000 kilometers underneath it, in a region the flare's particles and radiation cannot reach. Charged particles from a flare are stopped in the upper photosphere. Radiation from a flare is absorbed in the same place. Neither penetrates a megameter of dense plasma. The candidate explanation involves the magnetic field structure itself. The flare occurs in a magnetic loop, and that loop does not begin at the surface. It is anchored deep in the convection zone, where the field is generated and where the flux tube rises from. If the reconnection event at the top of the loop produces a rapid mechanical response along the whole structure, then a rearrangement high in the atmosphere could deliver a shove far below, transmitted down the field rather than through the gas. That is plausible in outline. It has not been demonstrated in detail, and it does not explain the selectivity, why some flares do this and most do not. There are correlations that hint at something. Sunquakes appear more often in association with white light flares, the kind bright enough to be visible against the ordinary photosphere, and with flares accompanying coronal mass ejections. That suggests a link to how deeply the flare deposits its energy. But the correlation is not tight enough to function as a rule, and it does not identify a mechanism. There is a broader difficulty lurking behind this that is worth acknowledging. The convection zone occupies the outer 30% of the Sun's radius, and it is where the magnetic field is generated, twisted and stored before it emerges. It is also the region we understand least well, because convection at these scales cannot be simulated from first principles with current computing. The range of scales involved, from the size of the whole zone down to the smallest turbulent eddies, spans too many orders of magnitude. A sunquake source at 1 megameter depth sits squarely inside that badly modeled region. It is not simply that we do not know what makes the wave. It is that the neighborhood where the wave is made is the part of the Sun our models are worst at. There is one appealing practical consequence. The waves from a sunquake pass through the subsurface structure of the active region that produced them, and they carry information about it. Some work has explored whether the seismic response of an active region could be read as a precursor, whether the Sun's ringing might warn us that a region is close to producing a large flare, rather than only confirming that it already has. Given that large flares and the mass ejections that accompany them can disable satellites, disrupt navigation systems and stress power grids, a warning of even a few hours would be worth having. But the basic question is where we started. Something rings the Sun like a struck bell after certain flares. The strike lands beneath a surface the flare cannot reach, and after more than a quarter of a century of watching, nobody can say what delivers the blow. That is inside the Sun. The next item is the space between the Sun and us, and it is visible from any dark field on a clear morning. Number 3. The dust above the horizon. Go somewhere genuinely dark, well away from towns, on a clear night in the right season. Look toward where the sun set, an hour or two after it has gone, or toward where it will rise, an hour or two before. If the conditions are right, you will see a faint triangular cone of light rising from the horizon, tilted along the same line the planets follow. That is the zodiacal light. Away from artificial illumination, it is brighter than the Milky Way. Most people alive today have never seen it, because it requires darkness that has become rare, but it is not a subtle phenomenon. It has been recorded for a very long time, and it was studied carefully in the 1680s by Giovanni Cassini and by Nicolas Fatio de Duillier, who correctly worked out what it was: sunlight scattering off an enormous population of small particles orbiting the Sun. The particles run from a few micrometers to about a millimeter across, spread through the inner solar system in a flattened cloud concentrated toward the plane of the planets. There is a faint counterpart directly opposite the Sun in the sky, called the Gegenschein, produced by dust-scattering light straight back the way it came. It is one of the hardest naked-eye phenomena to observe. There is one crucial fact about this cloud. It cannot be old. Small particles in orbit around the Sun do not stay in orbit indefinitely. They absorb sunlight on the side facing the Sun and re-radiate it in all directions, and because they are moving, that re-radiation carries away slightly more momentum in the direction of travel than against it. The result is a very gentle drag. It is called the Poynting-Robertson effect, and for a millimeter-sized grain at Earth's distance, it removes the particle from its orbit in roughly 100,000 years. Against the 4.5 billion year age of the solar system, that is instantaneous. The zodiacal cloud is not left over from the beginning. It is being continuously resupplied, right now, by something. For most of the 20th century, the answer was settled. The dust comes from comets, which shed material every time they pass near the sun, and from collisions in the asteroid belt, which grind existing bodies into debris. The dust then spirals slowly inward and is eventually vaporized near the sun. Supply from outside drained toward the center. That model was refined for decades and is built into how the infrared sky background is calculated for every space telescope, because zodiacal dust glows in the infrared and sets a brightness floor that no instrument can see beneath. Then Juno measured it by accident. Juno launched in 2011 and spent 5 years cruising from Earth to Jupiter. Like every spacecraft, it carried star cameras, small telescopes that photograph the sky continuously and compare what they see against a catalogue to determine which way the spacecraft is pointing. Juno's cameras kept recording bright streaks that were not stars. The explanation, when it was worked out, was unexpected. The streaks were pieces of Juno's own solar panels. Juno's arrays are enormous, spanning about 20 meters in total, because Jupiter receives roughly 4% of the sunlight Earth does, and the spacecraft needed every square meter it could carry. That enormous area was being struck by dust grains, and each impact was chipping off small fragments of the panel structure, which tumbled away and caught the sunlight as they went. The cameras were photographing the debris from the impacts, which meant the team had, entirely unintentionally, the largest dust detector ever flown. Not a dedicated instrument with a small collecting area, but 20 square meters of spacecraft moving through the solar system for 5 years, registering every significant hit. Counting those impacts along the cruise trajectory produced the first direct map of how interplanetary dust is distributed across the inner solar system. John Jurgensen and colleagues published the result in 2021. It did not match. The impacts began abruptly near the orbit of Mars. They ended near the 4:1 orbital resonance with Jupiter. And the inclination distribution of the dust, how it was spread above and below the plane, matched the orbital plane of Mars, rather than the ecliptic or the broader inclination spread of the asteroid belt. The straightforward reading is that the dust producing the zodiacal light is coming from Mars, which is a problem because there is no way for it to get off Mars. The planet's escape velocity is 5 kilometers per second. Global dust storms lift material to 80 kilometers altitude, which sounds impressive and is nowhere near sufficient. It is not a question of height but of speed, and nothing in Martian meteorology accelerates dust to a fraction of what is needed. The authors said so plainly in the paper. The observations point at Mars, and the mechanism by which the dust escapes is unaccounted for. It is worth spelling out why the inclination measurement carries so much weight, because it is the part of the result that is hardest to argue with. Where a population of small bodies came from is written into the tilts of their orbits. Dust ground off asteroids inherits the inclination spread of the asteroid belt, which is broad. The belt is not flat, and its members are scattered several degrees either side of the plane. Dust shed by comets inherits the inclinations of comets, which are broader still, and in the case of long-period comets, essentially random. Dust from a single planet inherits that planet's orbital plane, tightly, because all of it started from the same place. The Juno data show a tight distribution matching the plane of Mars. That is not the fingerprint of a mixture. It is the fingerprint of a source. There is a second constraint hiding in the sharpness of the boundaries. The impacts do not fade in gradually as the spacecraft moves outward. They begin near Mars and stop near a specific orbital resonance with Jupiter, a location where Jupiter's gravity repeatedly nudges particles in the same direction each orbit and eventually removes them. A cloud with an inner source and an outer removal boundary is a coherent physical picture. It is simply a different one from the one we had. It has not been settled since. Comparisons of the Juno impact counts against established dynamical meteoroid models find real differences in the expected rates for both conventional zodiacal dust and for Mars origin particles. Some analyses argue the data are better explained by a mixture of sources or by the spacecraft's own local environment rather than the ambient population. Others take the inclination signature seriously as a genuine constraint that any model has to reproduce. What is not in dispute is that the dataset does not comfortably match the picture that was in place before it arrived. The stakes are not only aesthetic. This dust sets the infrared brightness floor for astronomy from within the solar system. It delivers somewhere between 50 and 100 tons of material into the Earth's atmosphere every day, almost all of it too small to make a visible meteor. And it is the local, close-up example of the debris disks we detect around other stars, disks whose brightness we use to infer collisional activity, and from that, to infer the presence of planets we cannot see. That inference is calibrated on the assumption that we understand our own. Parker Solar Probe has now observed the inner edge of the cloud, where the grains are heated past the point of survival and vaporize, at a distance of roughly 19 solar radii. That boundary had been predicted for decades and was only confirmed recently. The inner edge is now measured. The outer source is less certain than it was 20 years ago. There is something worth noticing in how this discovery happened, because it recurs across this list. Nobody proposed a mission to map interplanetary dust. Nobody would have funded one. The science case is real but modest, and the instrument would have been small. What produced the measurement was a spacecraft built for an entirely different purpose, carrying enormous solar panels for an entirely different reason, with navigation cameras pointed at the sky for an entirely different reason, again, and someone noticing that the streaks in the starfield were not noise. Several of the mysteries on this list were found the same way, in data taken for something else, by someone who did not look away from the anomaly. That is the dust around the Sun. The second item on this list is the Sun itself, and specifically, the direction it is pointing. Number 2, the star is leaning. The solar system formed from a cloud of gas and dust that collapsed under its own gravity and, because it was rotating, flattened into a disk. That is not a guess. It is the standard model. It was proposed in outline in the 18th century, and it has been confirmed in detail by direct observation of other systems forming right now. Young stars surrounded by flat disks of gas and dust, some of them with gaps carved by planets that are still assembling. The Sun formed at the center of that disk. The planets formed within it. Both came from the same rotating structure, which means both inherited their angular momentum from the same source. So the Sun's spin axis and the orbital plane of the planets should line up. Not approximately, precisely. There is nothing in the formation picture that would separate them. The planets do behave. Their orbital planes cluster tightly around what is called the invariable plane, which is the plane defined by the total angular momentum of the entire solar system. That plane is dominated by Jupiter, which carries about 60% of the system's orbital angular momentum, despite being 1,000th of the Sun's mass. Measured against it, the 8 planets have a root mean square inclination slightly under 1 degree. 8 bodies, formed over hundreds of millions of years, at distances ranging from 58 million to 4.5 billion kilometers, agree with each other to within a degree. The Sun does not. Its rotation axis is tilted about 6 degrees away from that plane. 6 degrees sounds like nothing. In everyday terms, it is nothing. It is the angle of a gentle ramp. In this context, it is enormous. It is roughly 6 times the scatter of the entire planetary system in an object that contains 99.8% of the mass. The Sun should not be a member of this distribution at all. It should define the reference frame that everything else is measured against. Instead, it is the outlier. The measurement is not in doubt. The Sun's rotation axis has been determined from sunspot tracking for centuries and from helioseismology for decades, and the number is solid. Relative to the ecliptic, Earth's orbital plane, the Sun's equator is inclined about 7¼ degrees. Relative to the invariable plane, which is the more meaningful comparison because it averages over all the planets, it is about 6. The explanations fall into 2 families, and neither is established. The first is that the misalignment was there from the start. Perhaps the collapsing cloud was lopsided, with the inner region that formed the Sun rotating on a slightly different axis from the outer region that formed the disk. Perhaps the Sun's birth cluster is responsible. Young stars form in groups, and a passing sibling star could have gravitationally tugged the outer disk into a different plane, while the inner region, where the Sun was assembling, held its original orientation. Perhaps a nearby star's radiation or wind stripped and torqued the disk asymmetrically. These are all plausible. They are also nearly untestable because the birth cluster dispersed 4.5 billion years ago and its members are now scattered across the galaxy. And they carry an awkward requirement. Whatever tilted the Sun relative to the disk had to leave the disk itself flat enough that 8 planets forming across an enormous range of distances all ended up within a degree of each other. The second family says something torqued the system afterwards. And the best-known version of that appeared in 2016. Elizabeth Bailey, Konstantin Batygin, and Michael Brown, working at Caltech, took the hypothesis of a distant, massive, inclined planet, proposed the same year to explain the clustered orbits of a group of distant objects beyond Neptune, and asked what else such a body would do. The answer is that over 4.5 billion years, it would exert a slow, steady, secular torque on the entire planetary system, gradually tipping the planet's collective orbital plane relative to the Sun's fixed spin axis. Their calculation reproduced the observed 6 degrees. It also reproduced the specific direction in which the Sun's pole points, starting from an initially aligned configuration. That is an unusually clean result. A hypothesis introduced to explain one thing turned out to predict, without adjustment, an unrelated number that had been sitting unexplained for decades. In physics, that pattern is normally a good sign. It is not confirmation, and it is important to be honest about why. The proposed planet has not been found. It has been searched for extensively, with wide-field surveys, with infrared searches, with reanalysis of archival data going back decades. Its inferred parameters have shifted several times as the sample of distant objects has grown, which is what happens when the evidence is a statistical pattern in a small and awkwardly selected sample. Some analyses argue that the orbital clustering which motivated the whole idea is a selection effect, a consequence of where surveys happen to point and when they happen to observe, rather than a real feature of the outer solar system. And objects discovered more recently sit on orbits that do not fit the predicted alignment. Meanwhile, the tilt has alternative explanations that require no new planet at all, and those explanations cannot be ruled out either. It helps to know how unusual, or not, the Sun's tilt is by galactic standards. Astronomers can measure spin-orbit alignment in other systems, using an effect that occurs when a planet transits its star. As the planet crosses, it blocks first the approaching limb, and then the receding one, distorting the star's spectral lines in a way that reveals the geometry. Applied across hundreds of systems, the results are startling. Some hot Jupiters orbit over the poles of their stars. Some orbit backwards, against the star's rotation. Misalignment is common out there. But those systems appear to have had violent histories, planets scattered onto new orbits by encounters with siblings or migrated inward by tidal interactions with a distant companion star. Ours does not look like that. Our planets are on nearly circular, nearly coplanar orbits, in a tidy arrangement that suggests very little has disturbed them since they formed. A quiet system with a tilted star is a stranger object than a chaotic system with a tilted star. There is a further detail about the Sun's rotation worth keeping in view. It does not turn as a solid body. The equator completes a rotation in about 25 days. The regions near the poles take closer to 35, and beneath the convection zone, the interior rotates almost rigidly. The transition between those two regimes is a thin shear layer called the tachocline, which is where the solar magnetic field is thought to be generated. So the axis we are describing as tilted is itself an average over a body whose parts rotate at different rates, in a structure whose origin is not fully explained either. The reason this belongs at number 2 is what it does to the framing of everything else. The solar system is the one planetary system we can measure directly and completely. We have sent spacecraft to every planet. We have landed on 3 worlds, and a comet and an asteroid. We have mapped the Sun's interior with helioseismology, measured its rotation at every latitude and every depth we can reach, and modeled its formation in exhaustive detail. Solar Orbiter has now returned the first images of the Sun's polar regions, which required leaving the plane of the planets entirely using a gravity assist at Venus. The poles had never been photographed before, because everything we build orbits in roughly the same plane the Sun's own equator declines to match. And the single most basic geometric fact about the whole arrangement, that a star and its planets should share an axis because they were made from the same spinning cloud, is wrong by 6 degrees. The leading explanation depends on an object nobody has seen. The territory gets better mapped, and the questions get worse. That has been the shape of this list from the beginning, and here at number 2, it is about as literal as it can be, the best measured star in existence, leaning. There is a small practical consequence that follows from the geometry, and it touches the Earth directly. The Sun's magnetic field is carried outward by the solar wind, and it drags with it an enormous rippled boundary called the heliospheric current sheet, which separates regions of opposite magnetic polarity. Because that sheet is tied to the Sun's rotation, and the Sun's rotation axis is tilted relative to the plane the planets orbit in, the sheet sweeps past the Earth in a pattern set by that tilt. Every crossing changes the local magnetic environment. It is a small effect, and it is measured routinely. It is also set by an angle nobody can account for. Everything on this list so far has been out there, at some distance, however small. The last item is not. Number 1. Where the heavy elements were made. Roughly half of every element heavier than iron was assembled by a single process, and nobody can say with confidence where that process happens. The process itself is not the mystery. It has a name and a mechanism, and both are well established. It is called rapid neutron capture, or the R process, and it works like this. Put an atomic nucleus into an environment flooded with free neutrons. Not just many neutrons, but an overwhelming density of them, and the nucleus will absorb them faster than it can radioactively decay. It climbs to configurations far more neutron-rich than anything stable, building outward from whatever seed nucleus it started with. Then the flood stops, and the swollen nuclei decay back towards stability, shedding electrons, and arrive as heavy elements. The conditions required are specific. Neutron densities above about 10 to the 20th per cubic centimeter, and the whole sequence has to run in under a second. Everything above iron on the periodic table that was not built by the slower, gentler S process inside giant stars was built this way. Iodine, xenon, europium, gold, platinum, lead, thorium, uranium. The question of where has been open since 1957, when Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle published the framework that organized stellar nucleosynthesis into the processes we still use. The R process was identified in that paper as necessary and unlocated. That was 69 years ago. The candidates have changed several times. Core collapse supernovae were the original favorite, and for a long time the answer seemed obvious. An exploding massive star produces an intense burst of neutrinos and a hot wind blowing off the newly formed neutron star, and that seemed like exactly the environment required. Detailed simulations as they improved through the 1990s and 2000s showed that the neutrino-driven wind is not neutron-rich enough. The neutrinos themselves convert neutrons into protons faster than the process can build. The candidate was largely abandoned. Neutron-star mergers took over. Two neutron stars orbiting each other lose energy to gravitational waves, spiral inward over hundreds of millions or billions of years, and finally collide. In that collision, material torn from two objects made almost entirely of neutrons is flung outward. It is difficult to imagine a more suitable environment. And in August of 2017, we watched one. On the 17th of August 2017, the LIGO detectors in the United States and Virgo in Italy registered a gravitational wave signal lasting about 100 seconds, the inspiral of two neutron stars. 1.7 seconds after the signal ended, gamma-ray satellites detected a short burst. Within 11 hours, telescopes had found the optical counterpart in a galaxy called NGC 4993, about 130 million light-years away. Something like 70 observatories eventually turned to look at it. Imagine the final second before that. Two objects, each roughly 20 kilometers across, each weighing more than the Sun, orbiting each other hundreds of times per second, so close that their surfaces are nearly touching. The gravitational waves they are shedding carry away energy at a rate that briefly exceeds the light output of every star in the observable universe. Tidal forces begin to shred them. A plume of material is thrown out, matter at nuclear density, decompressing violently, a flood of free neutrons at a concentration that has no terrestrial comparison. Into that flood, seed nuclei begin capturing. They climb the chart faster than they can decay, absorbing neutron after neutron, becoming enormously unstable and continuing anyway. Then the flood thins, and the whole population of swollen nuclei decays back down toward stability, arriving as gold and platinum and uranium. And then, 130 million years later, in a control room on Earth, an alert goes out, and people start pointing telescopes. What they saw is called a kilonova, and it behaved exactly as predicted. The glow brightened and then reddened over days, which is the specific signature of freshly made heavy elements. Lanthanide-rich material is extraordinarily opaque, so it traps light and re-emits it at longer wavelengths. Estimates put the mass of heavy elements produced at several times the mass of the Earth. It was the cleanest identification of a nucleosynthesis site ever obtained. It is also not enough, and the reasons are specific and stubborn. The first is timing. Neutron star mergers are slow to arrive. You need two massive stars in a binary, both of which must explode without disrupting the pair, both of which must leave neutron stars rather than black holes, and then the two must spiral together through gravitational wave emission, which for typical separations takes hundreds of millions to billions of years. But the oldest stars in the Milky Way's halo, which formed within a few 100 million years of the galaxy's beginning, already contain our process elements. Some of them contain a great deal. There are extremely metal-poor stars, with europium abundances comparable to the Sun's, while carrying perhaps 1,000th of the Sun's iron. Mergers cannot have delivered that. There was not time. Something fast was making these elements when the galaxy was very young. The second problem is what happens when you try to fill that gap. Two prompt candidates have been proposed, both arriving within a few million years of star formation rather than billions. Collapsars, in which a rapidly rotating massive star collapses directly to a black hole and neutron-rich material is ejected from the accretion disk that forms around it. And magnetorotational supernovae, in which extreme magnetic fields in a rotating, collapsing core launch neutron-rich jets before the neutrinos can do their damage. Both work for the lighter R-process elements. Neither works for the heaviest. Detailed simulations, particularly ones that include the electrical resistivity of the plasma properly, show that in collapsars, the strong magnetic fields drive the outflow away before enough neutron capture has taken place. The material escapes before it can finish climbing. Collapsar outflows come out too neutron-poor to reach the third abundance peak, which is the platinum and gold region, and they do not make the actinides at all. Which brings us to the third problem, and it is the sharpest. There is a category of very old, very metal-poor stars called actinide boost stars. Their thorium and uranium abundances are elevated relative to europium by factors that no single production model reproduces, while other stars, with otherwise identical R-process abundance patterns across dozens of elements, show no boost whatsoever. Detailed studies of individual actinide boost stars using the highest resolution spectrographs available on large telescopes keep confirming the pattern rather than dissolving it. New examples continue to be found, including in the debris of a dwarf galaxy the Milky Way swallowed long ago. Two stars can match each other element for element across the whole R-process pattern and differ by a large factor in thorium. That implies at least two distinct environments producing chemically similar but not identical output. Which means the question of the site is not one question, it is several. There is one more complication, and it comes from an unexpectedly small scale. Astronomers have measured R-process enrichment within a single globular cluster and found it varies from star to star, a population-dependent scatter among stars that formed in the same place at very nearly the same time, from what should have been the same gas. That is not what you expect if the enrichment came from a well-mixed reservoir. It suggests the enriching events were rare and localized enough that different parts of a single collapsing cloud received different amounts. Rare, powerful, patchy events are precisely what mergers look like, and precisely what makes them so hard to account for statistically. The measuring stick in all of this is europium. It is used as the standard tracer of R-process enrichment because almost all of it, in the Sun and in every star we can measure, comes from that process and no other. That makes it a clean signal in a stellar spectrum. It is also why the actinide problem is stated as a ratio, thorium relative to europium, uranium relative to europium. When two stars agree on europium and disagree on thorium, the disagreement cannot be hidden in a difference of overall enrichment. It has to be a difference in what made the material. Here is the honest summary. Neutron star mergers certainly make heavy elements. We watched it happen. They probably make a large share of them in the present-day galaxy. They cannot account for the early universe, and they cannot account for the actinide variation. Prompt sources probably contributed early, and probably do not reach the heaviest elements. The relative contribution of each remains unresolved. And the origin of thorium and uranium specifically has no confirmed site at all. The reason this closes the list is not the physics. It is the location. Every other item we have covered is somewhere else. The cosmic web, a cluster of galaxies, a detector in orbit, a neutron star 12 million light-years away, the center of our galaxy, a comet, a moon, another planet, the moon, the sun, the dust between here and there, all of it out at some distance, however small the distance became as we counted down. This one is not. The iodine in a thyroid gland, without which the body cannot regulate its own metabolism, and the lack of which is still one of the most common preventable causes of developmental harm on Earth, was made by rapid neutron capture. So was the thorium and uranium distributed through the Earth's interior, whose slow radioactive decay supplies a substantial fraction of the heat, keeping the outer core molten, which drives the convection that generates the magnetic field, which deflects the solar wind that would otherwise have stripped the atmosphere away long ago. The gold in a wedding ring, the platinum in a catalytic converter. Every one of those atoms was assembled in less than a second in an environment we have not conclusively identified, and then delivered here. Some of it arrived while still radioactive. Certain short-lived isotopes were still decaying when the Earth formed, and their daughter products are locked in meteorites, which lets us calculate how recently before the Sun's birth the last nearby R-process event occurred. We can date the delivery more precisely than we can name the source. There is progress coming. Gravitational wave detectors are improving, and the next generation, Cosmic Explorer and the Einstein telescope, should observe enough neutron star mergers to measure the population's contribution directly rather than by extrapolating from a single event. Deep spectroscopic surveys keep turning up new actinide boost stars, and each one narrows the range of environments that could produce them. Within a few decades, the accounting may close. But the question asked in 1957, where were the heaviest elements assembled, is, in its full form, still unanswered. That is the shape of this list, and it is why the order ran the way it did. We began with the largest structure in the universe, in territory so poorly surveyed that not understanding it seemed reasonable. We ended in the palm of a hand. The territory got better mapped at every step, and the questions did not get easier. They got closer. None of this is cause for alarm. An unanswered question is not a threat. It is simply work that has not been finished yet, and most of it is being worked on right now by people who will probably not live to see it closed. That is the ordinary condition of the subject. The universe is not obliged to be finished being explained, and it is not. Somewhere overhead, the same processes are running that ran before there was anyone to notice them. Sleep well, and good night.